Hello, everyone. Welcome to the PhD-Teach-PhD workshop. And here I will present the foundations of deep learning theory. So in this workshop, I aim to give a gentle introduction to the deep learning theory from three aspects: the approximation, optimization, and the generalization. The contents of these slides are based on the lecture notes of deep learning theory written by Martin Tagarsky. Okay, so this is the outline of this workshop. First, I will give an introduction of deep learning, and then followed by the three aspects, as I said, approximation, optimization, and generalization. And finally, I will end up with a concrete example that connects the optimization and generalization to show the interplays between these three parts. This is the neural tangent kernel. So I think we can start with the introduction part. So we know that recent years has witnessed the success of the deep learning in so many areas. For example, the self-driving, machine translation, and game playing. But why does the deep learning work so well? Is still not completely understood, especially in the mathematical theory. So to understand the theory behind the practical success of deep learning, we need to first understand what is deep learning doing. And then let's see why the approximation, optimization, and generalization are the three important aspects. Okay, so for the first thing is that the task of deep learning. So in one sentence, the deep learning is doing prediction on some data points. So for example, if we are given an image, we want to know what class is this image in, and also like we want to predict the tomorrow's weather. So this is what deep learning is doing, and usually method is using the supervised learning method based on the observed data set. So basically, this is a method that learns a function that maps an input to an output based on example input-output pairs. And this learner model, we ideally expect that the learner model can correctly determine the class labels for unseen data set. Okay. And next, let's formalize the statement just now while using the mathematical statistical language. So here we are given a data distribution D. This is a jointly distribution with input X and the label Y. So we suppose that the data distribution is there exists an underlying target function f star such that the data is generated by f star. So that means y is equal to f star x for any xy in this data distribution. So the task of deep learning, as I said, is to make prediction. Usually in practice, the f star is unknown, so we want to find a mapping based on observed data set. So to do that, we first define a hypothesis space denoted by F. This hypothesis space consists of all the possible candidate functions that we want to choose from. So for example, the hypothesis space can be a linear model given by mapping from X to a linear function W transpose X plus B. Here W is the weight and B is the bias. So when translating into the mathematical language, we want to find linear functions from this linear model to approximate f star, namely to have the same can map X to Y exactly. So as illustrated in this figure, this is the target function f star, and this is the hypothesis space f consists of all the candidate functions. So the task of deep learning is that to choose one function f tilde that is closest to f star. So this is what the approximation is doing. And mathematically speaking, we want to minimize expected loss given by this form. This is the expectation of the loss function with respect to fx and y, and xy is in the distribution D. So and in this figure, we can show this is basically the approximation error. And if we are lucky enough, if the f star is just inside this hypothesis space f, then the approximation error can be 0, because we can actually find a candidate function in this hypothesis space to have the same effect as f star, and this expected risk can be 0. But usually we are not lucky enough, because usually the f star is very complicated, and it requires that the hypothesis space is large enough. Okay, now it turns to the optimization part. So since we have only finite access to the training data, and we cannot see we do not know the data distribution, therefore we cannot directly minimize expected population risk. So how to do that? The idea of supervised learning is through the empirical risk minimization. So that is given a finite size of training data set, we say xi, yi. So this is with size n. And the empirical risk minimization is to minimize the empirical loss on observed data. Mathematically written, this is written by this formulation. So again, we want to choose a function in this hypothesis space f to minimize empirical risk on the training data. So usually in the deep learning, how to minimize this function is through some optimization algorithms. For example, the optimization algorithm that we are familiar with, the gradient descent, stochastic gradient descent, and obviously to iteratively update the parameter from the initialization until convergence. So this procedure is shown in this figure. So this is a target function, but usually it's unknown, and we want to find the f tilde. This is approximation procedure. So to minimize empirical risk, we are given the training set. We start from the initialization and using some optimization algorithm to train this loss function. And suppose we stop here, then we have a learner model. This is the model that we can get. And how the learner model performed in this training data set, then this is the optimization error. So usually if our optimization algorithm is powerful enough, then ideally this optimization error can be 0. So now we achieved here the learner model, but the target of the deep learning is to make an exact prediction on unseen data. So basically we want that our learner model can also perform well on the test data or the unseen data. So basically then this is the empirical risk minimizer. This is the minimizer of the expected loss. So basically, when these two also are closes. And this red dashed line implies the generalization error. And how close are these two functions measures the generalization error. So based on this, we can see that the approximation, optimization, and generalization comprise the foundations of deep learning.
I missed the part. So what's the learned model and at?
This one?
Yeah, and then
this is the empirical risk minimizer. Meaning that this is the best model in the training data.
And the learned model?
The learned model is to minimize empirical risk. We need to use some optimization algorithm.
So
but usually we cannot get into this part, because if the empirical risk is very complicated, then it's not easy to optimize to the global minimum.
So the learned model is the model that ideally you would obtain the minimum, but you cannot.
Yeah. This is obtained by some optimization algorithm.
Yeah.
But the optimization is not the easiest thing. Okay. Okay, so let's begin with the first part, approximation part. So as I introduced, there is a underlying target function f star. Usually this is the function that we don't know. So how to measure the approximation of a function if we do not know a data distribution? Usually the idea is that we compare the compare the norm, one of the norm between the hypothesis space F to the target function f star. So this norm can be whatever you want. For example, it can be LP norm. You treat this function in the LP space, or you can define whatever you want. So for LP norm, this is usually defined as an integral between the difference of these functions. So usually, if the norm is the infinite norm is 0, that means we can find a function. We can find a function f in the hypothesis space to 100% approximate the target function f star. But we know that usually the f star is unknown. So how to measure the approximation ability of the function class? The idea is that to replace the f star with each continuous function. Because we know that continuous function is very general and representative, and usually we can say almost all of the target function are continuous. So if a hypothesis space contains all the continuous function, then we can say this is good, because we can get 0 approximation error for any function. We can find exactly one candidate function to approximate the target function.
I didn't understand.
Who is what? This one?
Yeah.
This is the infinite, meaning that the minimum, you can understand this as a minimum mean, because this is a infinite set, so we can only the minimum then moves to the infinite.
But the f star not necessarily is continuous, right? F star, the true function, not necessarily is continuous.
Yeah, f star is the target function that usually we don't know what it looks like. So the idea to measure the approximation ability is to compare with the continuous function. If the hypothesis space can approximate any continuous function, then this is very good.
But if f star is not continuous?
Because uncontinuous function is not common in practice. I think in the deep learning we seldom deal with the uncontinuous case. I think continuous is enough. Uncontinuous is not that common. So
no, I mean when you want to approximate a graph, graphs are usually not continuous. They're defined in discrete space.
Graph is uncontinuous, is it?
I don't know. I think so. Because the nodes, an edge can only connect a discrete set of nodes, so you cannot have like half an edge.
It is the case then.
But I don't know. Like, maybe we can move on. Maybe we can talk about that.
Okay, I know what you mean. So you mean that for graph, the domain is not continuous.
Yeah,
right. But we can make the domain continuous to connect all the discontinuous points, and then make the function continuous. Okay. So this is the idea for universal approximation, to compare the function with all the continuous functions. And the definition basically states that if a hypothesis space is a universal approximator, that means for every continuous function, we can find at least one candidate function to approximate this continuous function with arbitrary small error. No matter what the continuous looks like, even though it oscillates, the function class can approximate this. Then this is called the universal approximator. So now the question is that what kind of hypothesis space or what kind of function class is a universal approximator? Usually we request the function class to be large enough to contain all the continuous functions. So let's think about the first example. Linear function. Is a linear function a universal approximator? Let's think about the question. Anyone? Sophie?
No.
No, why?
We can approximate, for example.
Right. A quadratic function, right?
Yeah.
Right. Linear function is not that powerful, because if we imagine that we have a.
Oh, you can use this, the pen there.
Can I?
Yeah.
Come on.
Sure, there's a way. You can find it out.
Function for.
Like when Xiaomia was presenting, she would click there and then appear some stuff.
Click where?
No, with your finger, you click on the screen.
Cannot right. Okay, so then you have to imagine it, because I cannot run. So imagine that there is a quadratic function. This is the x-axis, this is the y-axis. We imagine that in one dimension, if this function is like this, right? Can you use a linear function to approximate the quadratic function? Can you? Yeah, no, right? Because we cannot approximate this projective function with arbitrary small error. So that means the linear function is not powerful enough. Okay, now let's look at the second example. Polynomial functions. Is polynomial function a universal approximator? Is it? Why?
There are some theorems given mathematics.
Okay, but intuitively, this is good enough, right? Because imagine that if we want to approximate a function, no matter what it looks like, if we sample some 100, 1,000 points in this function, then we can use like 100-degree polynomials to 100% fit this function, right? So intuitively, polynomial function is good.
As a class, okay, choose one if you want, but if you already picked it and want one from three, let's say 5. Then
Yeah. Okay, yeah. So here the polynomial function class does not have the requirement for degree. You can choose any degree you want.
So that is even linear functions should be good. You can have like
Are you sure?
you can have a piecewise
Linear, but for linear function, you need this to be continuous. Yeah. Linear is just, so in one dimension case, this is like.
This was the function.
Piecewise, it's not.
This was the linear, it's not linear.
It's not linear. It's so for each small interval, this is linear, but this is not continuous. See?
Linear functions are only of the form ax.
How do I define the linear model? Do you still remember linear models? This is a linear function. Okay. So yeah, just as you said, this is determined. This is guaranteed by the so-called Stone-Weierstrass theorem. So this theorem explicitly constructs a called Bernstein polynomial to approximate any continuous function. But I will not go into the detail of this because our focus is on the deep learning. So the question is that is neural network a universal approximation? This is a non-trivial question. And here I want to highlight. I want to give some high-level understanding on the neural networks. So first, let's look at what is a neural network. So I think maybe all of you guys know what is neural network. So basically, okay, there is a question in Zoom. Can periodic functions like sine and cosine be approximated by? Okay, this is a good question. So Ruofan asked that, can the periodic function like sine and cosine functions be approximated by polynomial functions? The answer is yes, because we have Taylor expansion. And if we restrict the periodic function in the compact set, then the Taylor expansion tells us we can approximate this function to arbitrary small error if we have larger degree. If we expand to the high order term. Is this clear?
So any function, so if you use the Taylor approximation, you can approximate any function with a polynomial. Is that what the Weierstrass theorem says?
Yeah, but the thing is that this requires that the function is analytic. Because this is the definition for analytic function, that if you restrict the function in a very small set, then analytic function tells you that you can use a Taylor expansion to approximate this analytic function. But here, the universal approximator is to compare all the continuous function. There exists some functions that is not analytic but continuous. So you cannot use a Taylor expansion to do that.
Can you give an example? Just sort of curious.
Okay, an example is that consider function, because I cannot right now. So consider function. This is non-analytic but continuous. So this is given by y equal to e to the minus 1 over x squared when x is not 0. When x is 0, this is 0. So this function looks like very oscillating near 0. This is continuous and also differentiable. C infinity differentiable. Because you can take the limit to verify this. But this is not analytic in 0. So this is one classic example that a function is continuous but not analytic. That means for this function, you cannot use Taylor expansion to approximate it. But you can use the Bernstein polynomials. This is guaranteed by the Stern-Weierstrass theorem. Okay. Okay, I think I can continue. So this is the structure for the neural network. Usually we have an input here. So basically the neural network function is a composition of a series of functions. Also maybe nonlinear. So when joining this picture, this is the input layer. We have some input. And this is some mapping, maybe linear, maybe not linear. Mapping to the first hidden layer to the second hidden layer, and there are many, many layers. And finally, we have an output here. So this is what does the neural network? Oh, okay, I can write here.
When you want.
Yeah, but the camera cannot see. Okay, I can write here. Okay, so this is the structure for the neural network. And now we give an explicit formulation for two-layer neural networks. This can be expressed in this form. Here, this in the item inside the bracket is the input layer to the hidden layer mapping. This is linear. It's a linear, and then we have activation function phi. Usually phi can be linear or nonlinear. For nonlinear activation, this contains like value sigmoid tension. And then we by some linear combination of this node, we get output. So this is the formulation for two-layer neural network. Okay, recall the important questions. Are neural networks universal approximators? The answer is yes. But why? How to understand these results? So I remember that some of you mentioned the piecewise function. So the idea is that for any continuous function, we can approximate the continuous function by a piecewise constant function. Okay, maybe you guys are lost, but I will use an example. That imagine that you are doing some numerical integral. We have a function, continuous function in 0, 1. This is x, this is y. So back to your high school math course. How do you compute the integral? I mean the area. How do you do that?
You approximate it in all rectangles.
Exactly. So the numerical method is to use a series of rectangular, right? Like this. Right, and then compute each area of this rectangle and sum it. Then we say this is approximately the integral for this function from 0 to 1. So why this method works? This is guaranteed that the series of rectangular can approximate this curve with arbitrary accuracy. The thing that we only need to do is to narrow the bound. Right, so the understanding is the same in the approximation of neural networks. So if we want to approximate this function, this continuous function, the idea to approximate is to consider this, a piecewise constant function. Like this. Step by step, for each step, this is a constant function. Right. So by the idea of computing the numerical integral, we know that this piecewise constant function can approximate this continuous function well. Okay. So now an interesting thing is that a piecewise constant function is exactly a two-layer neural network. Do you believe that? Okay, this is easy. So we know that for a continuous function, this is Lipschitz in a compact set. That means if two inputs are close, then the function value will be close. It's like compressed in the compact set. So the idea is that we can partition the x-axis to be very small, like 1 over epsilon. We have 1 over epsilon partitions. So this is basically epsilon, 2 epsilon, 3 epsilon, and finally we go to 1. We partition the x-axis. And then if the continuous function is 1 Lipschitz, that means for any epsilon bar, the function value is less than or equal to epsilon. So this is less than epsilon. So here we construct a piecewise constant function to approximate this function with error less than or equal to epsilon. So how to express this piecewise constant function? Well, this is not hard because this is like we can write it down. If x is in from 0 to 1, if this is in 0 to epsilon, then the function value we take to be f0. If this is in 2 epsilon, then this is given by f epsilon. And we move on. If this is 1 minus, for example, m epsilon, then this is given by, this is a piecewise constant function, we say G. Okay. So now let's think about how to express the GX into a 2-layer neural network. I'm not. Oh, you stop sharing, right?
You're writing.
Okay. So now let's think about how to write GX into a 2-layer neural network. We call that the 2-layer neural network is like the form. If we have m hidden layer or m hidden units, then this is like CI with some activation function phi. AI transpose X plus BI. So now our task is to find CI, AI, BI to express this piecewise constant function. Okay, let's see. This can be expressed in this form. This can be expressed by some indicator function. So the indicator function means that if x is greater than or equal to AI, then this is 1, otherwise this is 0. So if we write it down, if x is greater than or equal to, or if 0 is less than x is less than AI, less than A1, then this is basically C1. If x is in A1 to A2, then basically this is C1 plus C2, etc. So to construct a 2-layer neural network to express this form,
the one of the first expression there on the left corner is fx, right? Gx.
this
No. There. Yeah, is this gx equals to that?
yeah, it's like a step function.
But GX is an approximation of the area or the.
This is the piecewise constant function that we want to approximate f.
You're approximating f.
Or maybe the notation, yeah. Okay, maybe here should be g, here should be f. But
okay. Let me just check. I'm just checking. All right.
okay, so here we can express this. This is exactly the piecewise constant functions. Right? As you can see, if x moves on from ai plus ai to ai plus 1, then this is basically c1 plus c2 plus c plus ci plus 1. So to match this function with this one, we can set c1 to f0 and c2 to f minus f0. And then this one minus the former one. Okay?
As the AI on the first line, anything to do with the AI.
This one. Then you can imagine this is just a one dimension because there is no transpose here. There's no bi. So it means phi aix is the indicator function.
So what he means that I is defined by x, the function, but it's not multiplying there.
Okay, so you mean that AI. Okay, so since for neural network, this is a linear mapping, right? But usually we can set the mapping to be nonlinear, like this. So this is the case for some input neuron maps to the hidden neuron. This is linear, but usually we can set it to be nonlinear. So this is a two-layer neural network for linear mapping from the first layer to the hidden layer. Okay, but generally we do not need this to be needed.
But usually in a neural network, you have the linear mapping plus the activation function that is non-linear. So in this case, maybe you could see as AIX as so AI would be 1 for the mapping.
Yeah.
The linear mapping and the non-linear mapping is the indicator function.
Yeah, also you can do that. But the problem is that this is AI times X, but this is indicator function with X greater than or equal to AI. Do I answer your question? Okay, so far so good. Okay, so we can see that for any continuous function, we can use the piecewise constant function to approximate it, and the piecewise function is exactly the two-layer neural network. Even though that this is kind of looks like uncommon because here use the indicator function, which is not commonly used in practice. So okay, but at least this is an example to show you that the power of neural network. So in the it's like this one. And this is what I write just now. Use the one if you want to approximate a function with absolute error, you can use 1 over absolute neurons. But since this is not a not a very good example because this does not match with the practice that we use. This is not indicator function is not commonly used. So now let's think about another case that you.
So if the objective would be to find the optimal AI, in this case, to try to approximate.
AI is just a segmentation for the x-axis into one over epsilon parts. The next example is more practical. That consider to use the inverse Fourier representation to approximate or represent any continuous function. Okay. So the idea for Fourier transform is to express a function, to express a function, to map a function into a space. I will not say this is a Hilbert space with Fourier basis. So usually for the Fourier series, okay, I think I should write here. To introduce the intuition for the Fourier transformation, in case that you are not familiar with. Okay, if we have a function fx, if we consider so usually the Hilbert space is an inner product space. And we have some basics. So for example, for the Fourier series, this is the Hilbert space is given by the sine and cosine function, sin x, sin 2x, cosine x, cosine 2x. And the inner product is given by the integral for x from negative pi to pi, and usually some constant 1 over c, normalized constant. We want this to be the integral to be 1. This means then basically these functions forms also normal basis. The Hilbert space is analog for the Euclidean space because we know that in Euclidean space, there is a question. If the dimension of x increases, does the derivation go through similarly by consider L2? Yes. This is a good question. If the dimension increase, then we need to also doing the same like the piecewise linear function to partition the space into different rectangular to approximate the function, and also by considering the L2 distance, right? But the problem is that if the dimension is that high, the requirement for the hidden neurons will dramatically increasing.
What are the bounds there? I can't see the integral.
Which
What
one?
are the boundaries?
This one?
0 and 1.
This is negative pi.
What?
Negative pi
Negative pi.
to pi. Okay, also because this is periodic with 2 pi periods, so you can also put it 0 to 2 pi. So we said these functions form also normal basis, and we know that if given that we have orthonormal basis, we can express any functions into some linear combination of this orthonormal basis. So this is the idea for Fourier series. And what if the function is not periodic? This is in the whole space RD. Then this is the idea for Fourier transformation, doing an integral with some basis function exponential, also the cosine and the sine function. So this is you can imagine this is a transformation to express the function from Euclidean space to a Hilbert space. Okay. And how to go back? The idea is to use the inverse Fourier transformation. So the inverse Fourier representation express the function gx with its Fourier constant g hat. The advantage is that by using the inverse Fourier representation, we can represent gx into this integral, and this integral can be approximated by some numerically some summation. Because recall that what do we do the numerical integral? Is it to sum the rectangular, to partition the area and sum the area of the rectangular? This is exactly given by this form. We partition the RD and then numerically compute this integral. So basically this is equal to the limit to the infinity summation.
Sorry, I didn't understand what does it have to do with what you wrote in the last line.
Here?
Yeah.
Okay, so now
What are you trying to?
for any fx, we can express fx with some linear combination of the basis ai sin ix plus bi cosine ix for I for 1 to infinity.
But what is that? Why did you do one over z sin x plus sin x equals 1?
This is the inner product.
So the
Inner product in the Hilbert space given by if f and g, the inner product is given by the integral. This is different from the inner product in Euclidean space, which is exactly taken the vector inner product. So this is another kind of inner product given by the integral. And then we can express the fx to be some basis function, and each coefficient ai and bi is given by some Fourier calculation. This is for the periodic function, and this is for the non-periodic function. Clear?
Yeah.
Okay, hope that you guys are not lost. So here by using the inverse Fourier representation, we write the function g, any continuous function into an infinite summation. So look at this form. This is exactly a 2-layer neural network with infinity arc. So recall that for a two-layer neural network is given by CI, AI plus BI. So in that case, this inverse for the right-hand side then correspond to CI CI equals to J hat WI. And phi is a mapping from X to X exponential to pi X. And AI then is equal to WI. BI is 0. So here we can see that this corresponds to the infinity width network with infinity number of hidden neurons. And this activation function seems to be more reasonable. I mean, more close to the practical use, because this is exactly what this is. If you expand this into this concept to pi x plus pi sine 2 pi x. If this is a real valued function, then this is just a 0. We ignore this. So that means this activation function is given by the cosine function, which is more practical than the indicator function, the first example that we list.
Why don't we just use the cosine function as an activation function? But we use the as an activation function.
Okay, this is a good question. So cosine function is a neural network class given by the with the cosine activation function is a universal approximator, as we showed here. So why do we not use the cosine activation function? Because approximation is not the only issue in deep learning. We have 3 issues: approximation, optimization, and generalization. Even though that cosine is good, universal approximator, but I tell you that ReLU, sigmoid, tanh are all universal approximators. The reason that we use ReLU is that it's good for optimization and generalization. Okay, because this example can be easily shown by the Fourier representation, but the approximation for the neural networks with ReLU or sigmoid, some other kind of activation function is still not completely understood. If you are interested, I will recommend the work by our US professor Zhou Weisheng. He did a very nice work in the approximation for ReLU neural network.
So when you do the Fourier transform, originally you don't use weights, right? When you're just doing the Fourier transform.
Yeah, there is no way. Just some integral from RD or RD. This is you can imagine this is the weight W.
Yeah, but like the original Fourier transform, we don't use weights. Do you use weights? Like in the classic Fourier transform?
There's no weight, I think.
Okay.
Yeah, just a function, and you can express this function to some linear combination of some into some other Hilbert space. This is another expression.
But when it's okay to add weights, like
yeah, it's okay. You can also add weights. Any question? Okay, if not, let's move to one more example. So I think there is there is someone that asking the question that what if we increase the dimension? What if we want to approximate a continuous function in 2D or larger dimension? So we know that piecewise constant functions are universal approximator, and neural networks is also a universal approximator. Then why don't we just use piecewise, but use neural? The key thing is that the piecewise constant function suffers the curse of dimensionality. So remember that in this construction, if we want to use piecewise constant function to approximate a continuous function, the number of hidden neurons requires to be with order 1 over epsilon, right? For example, if we want to approximate this function with 0.1 error, we need like 10 hidden neurons, 10 hyperparameters, or you can see. But what if we go to the high dimension like 2 or even RD? Then the case becomes that M should order like 1 over epsilon to the D power to make sure in each direction the rectangular is less, the rectangular has, by the Lipschitz continuous, can induce the function value to be less than or equal to 1 epsilon. So this is the case for high dimension. So now we want to approximate a function using piecewise constant function. If we denote D to be the dimensionality of the problem, M to be the free parameter in the model, then M should be ordered like 1 over epsilon to the D power. That means if we want to reduce an error by a factor of 10, then we need to increase the number of parameters by a factor of 10 to the D. This is a bad thing, because usually in deep learning we deal with the case with D hundreds, thousands. So if we just want to reduce the error a little bit, we need to exponentially increase the number of parameters. This is not what we want, because the computation cost is so high. And now I tell you that the neural networks can be the worst case of curse of dimensionality. So why is this the case? Here I will introduce a very important result by Baron in 1993. So in this work, Baron considered a 2-layer sigmoid neural network on RD. Recall this is the form for 2-layer neural network. Here, phi is a sigmoid function given by 1 over 1 plus e into minus x. For this 2-layer sigmoid neural network, Baron proved that for any continuous function and target error, you only need the Baron norm of G over epsilon squared number of parameters to approximate G. The Baron norm is defined by this form. Okay, you can just ignore this. And usually for some continuous function, the Baron norm is not that bad, because this example shows that for Gaussian radius basis function, this one, this is an RD function, the Baron norm scale that is square root D. So this means to approximate the Gaussian RBF functions, the number of neurons is scale like square root d over epsilon squared. Recall that for piecewise function, the number of neurons scale like 1 over epsilon to the power d. So we can see that this for neural network, the number of neurons is square root d increasing, but this one is exponentially increasing. So this is one advantage for the neural network. That is, the neural network can beat the worst case of curse of dimensionality.
So the mean by worst case it means like it's worse than the exponential one.
No, the worst case means that you need at most, because you can consider the worst case too. So at most you need this less than or equal to, but also you can also like use smaller some smaller m if the G is good. Is simple if G is simple. Okay. For example, if G is just a linear function, then of course you do not need to use this number of hyperparameters. So you can just use one parameters. Okay, so this worst case means that the worst case on the continuous function, the worst case of approximation.
Yes, then
But just now for the exponential equation, it's for any function, but this one is for function.
Yeah, this is the case that I list here. But there are some other examples that for any continuous function, this can be small.
Extended question: What makes the neural network so special that can apply the theorem to improve the?
Okay, so this is a good question. You require me to introduce the high-level proof. I will try to simplify the description. So the idea is that similar to the inverse Fourier transformation, right? Imagine that you can express any continuous function into the infinite with neural network with cosine activation. And then there is some connection between the cosine activation to the sigmoid. If you consider by doing some transformations. And then the last thing is to do some perturbation analysis. So this is related to the Fourier transformation. And Baron defines such a Baron norm.
So what it means is that like the lowest amount of dimension that I can have is given by the expression that the expression there in the board. Like if I want if I'm considering a universal approximator, the least amount of dimension that I need to approximate that function would be that one that's in the board.
The most, not the least. Because M should.
But like the 1 over epsilon to the power of t is bigger.
Oh, it's the worst case is.
That was bigger than the one on top, right?
Yeah, especially when D is very large. This is, for example, if epsilon is 0.1, then this is like 10 to the D. This is like 100 square root D.
Yeah, so that's not the worst case 100 times square root of t. Because the worst case is 10 to the power of.
No, the worst case means that for the worst continuous function, given this number of hidden neurons, you can approximate it. This is the worst case means. So if for your case, if D is very large, then this actually is very large than the former one. So that means for neural network, it only requires a small number of hidden neurons to approximate a continuous function. Any question? Okay. If no question, I will recommend some further readings. This works consider different kind of architecture of neural networks. For example, Liu, for example, sigmoid to analyze the approximation ability for. I think maybe we can have a 5 minutes break. And we can go back at 11. Okay.
Should list the full name of the unit instead of
I think he has it.
a link.
Can you share the slide? Are you sharing the slide after?
Okay.
No. So what I mean here is this one, 100. Let's say D is 2. D is 4. So this will be 100 times 2 would be 200.
Yeah, then this is good.
Then this is better than this, no?
This is better than this. This is 100. This is 100 square root.
No, 4. 10 to the
Oh,
power of 4.
Then this is good.
This is better.
Yeah, because this
So
requires.
if the number of dimensions increase,
Yeah.
then this is better, no?
Yeah.
So how can this be the worst case?
No, I mean the worst case is worst case means that the worst case for the continuous function, given a specific function class. So this 100 square root is
So worst case considering considering this class of functions.
yeah. Consider this.
You may. Yeah, I think the time is late.
Yeah.
Since you reached the.
I only finished the
17
first part of approximation part.
That's good. Like doing
should
well.
be clear.
Are you clear about the?
So this is
Too clear, too details, but I think you cannot. You cannot.
You cannot
finish
cover
the-
all the
yeah.
materials.
but like let's try to see if I can understand. So like for the worst case of this approximation, gx equals this, then this is the worst you can get. Is that what you mean?
No. I mean the worst case is that okay, if the continuous function is very complicated.
Yeah.
So intuitively, you need compared to this function.
Yeah.
So for this continuous function, you need like 1 neuron, and for this function,
Yeah.
you need 100.
Yeah,
So
yeah.
this is the worst case.
Yeah.
100.
Yeah.
Yeah, this is what I mean.
Worst.
Because you need to approximate any continuous function.
Okay. But then the worst case for if I was using the piecewise would be this one, no?
Yeah, this will be this one.
Because I can approximate anyone.
Yeah, anyone, because
So because this is better, so this is better than
Yeah.
this. Yeah.
this is any continuous function.
But this is better. This is better than this one.
Yeah,
Is better
yeah,
than this,
yeah,
right?
yeah, correct.
So the worst case, because now the boundary has been reduced from this
Yeah,
to this,
yeah,
right?
yeah,
But
correct.
because any piecewise linear approximation is also a neural network
Yeah,
that you saw.
but the neural network is with activation function that is not commonly
Yeah.
used for indicator functions.
So
But
this
here this is
also
the
apply-
sigmoid.
Oh, this is a sigmoid.
Yeah, sigmoid.
Okay.
Yeah.
All right. By the way, you can write here. You write. How did you do that?
Cannot.
No. How did you do that? Appears the stuff. Sometimes you click here, then it appears something.
Oh, I don't know.
Here, click menu, and then now you can write.
No, cannot.
No. Then you can write now. Maybe try again. Does it work now?
No. Okay, no man, I can use this one.
But it should work, right?
How to go back?
No.
But it's not sharing.
There it's coming.
Oh, okay.
Or if I try a question, you can just keep write it down, then you can talk later.
Okay.
I don't know how much time you have, how many slides you have. Just let me.
对，本来我是计划的是这个，再接着，这个它是 open open。确实，真的，只有一天讲完。嗯？
送你的 link，如果送的 link 是需要，就是给他一个 meeting ID。哎呀，我这也是硬的。
我怎么发？
你就开那个，
哦，发这个吧。
发给我也行，我发给他。
你收到过这个邮件？
没有，他说 register 啊。
不用啊，你就点这个链接就行了呀。
点这个哦。
对啊，然后你输名字就行了。Okay, I think okay, I think I can start now. So let's have a quick recap. What we talked just now? So we covered the approximation part, and we showed that the neural network can be the curse of dimensionality in approximating a continuous function. This is the advantage compared to different type of universal approximators. So now the problem is that given that neural networks can approximate a continuous function, but the problem is that how can we find the best approximator? Especially we only have access to a finite set of training data. We cannot see what the data distribution is, and we do not know the underlying target function of star. So now we need the optimization algorithm. Okay, so as we said, the universal approximation property is existence result, but it does not tell us how to find a good approximator efficiently. So now we call this illustrative figure. If we want to, so now we want to optimize empirical loss in the observed training data. How to do that is that we given an initialization and using some optimization algorithm to train until it stops to some learned model. And the optimization error is given by how far away is the learned model from the empirical risk minimizer. So to formalize this intuition, we just list the formulation here with the purpose of ERM is to minimize empirical risk given the training data xi, yi for I from 1 to n. And here the L is the loss function, usually such as the squared loss, such as the cross entropy loss. And this loss function, if this is 0, then that means the learned model F can 100% fit the data, training data. Okay, so a common, maybe the most popular optimization algorithms to minimize this loss function is by some gradient methods, such as gradient descent, stochastic gradient descent, or some adaptive methods such as adapt. Okay, so if f is a parametric functions with respect to some parameter w, then the gradient descent iteration is exactly given by wt plus 1 equal to wt minus eta times the gradient direction. And we start from t to t equal to 0, start from initialization w0 with step size eta. But in practice training, usually we have a very large number of training data. To compute the gradient over all the training data is a computation cost. So usually we can also consider the stochastic gradient descent, that we sample the mini batch of the training data and compute this gradient and use this gradient as an iteration direction. So basically this is the formulation is like this one. QB is a batch size, and BT contains B distinct instances in 1 to n. And the gradient is computed only in this batch. So as you can imagine, for SGD, since the gradient is not exactly the gradient in the whole data set, so the function, so the iteration or the trajectory will be oscillates. But for gradient descent, since you use the full batch, use the full information of gradient, then the trajectory is very clean, just straightforward. However, for SGD, you only need the computation cost is lower than the gradient descent, so usually the SGD is more efficient than GD. So now the problem is that given an optimization algorithm, for example, GD or SGD, when we are optimizing an empirical risk, can we? Well, we want that optimization algorithm can return the local minimum or global minimum to get a good learner model. But this is not always the case, because sometimes if the loss is very complicated, then maybe the task is very hard for the GD or SGD. So the first question is that, can this algorithm return the local global minimum? This involves with the loss landscape analysis. If the loss landscape is very simple, is very simple. For example, if this is a convex loss, then yeah, you can just use GD to achieve the global minimum here. But if this loss is very complicated, or this is a one-dimensional case, maybe you cannot see that this is complicated. So maybe sometimes for high dimension loss landscape, it can be very complicated and not easy for GD or SGD to get a global minimum. So this is optimization problem. And also the next fundamental question is that we have suppose that we stopped the optimization algorithm and we obtain a learner model. So the question is that, does the minimum have small population risk? That is to say, does the learner model performs also well on the unseen data or on the tested data? And for this question, I will introduce the so-called notion implicit bias. Okay, so now let's firstly look at the loss landscape and analysis. Oh, okay. So before that, I will use another notion, gradient flow, to replace the gradient descent. This is to simplify the analysis, because for gradient descent, if we consider a limiting case that when the learning rate goes to 0, then the gradient descent reduces to some differential equation. This is what we call the gradient flow. So to see this, we again write this gradient descent formulation, and we divided both sides by eta. Eta is learning rate. So consider the case that when the learning rate tends to 0, goes to 0, then this is 0. This is also goes to 0. So this is like the derivative. And now we can just simply write it like the derivative. If we treat this discrete iteration as a continuous dynamics for t from 0 to infinity. If this is a continuous dynamics, for example, this is a continuous curve, then we take the derivative of the parameter dwt over dt. Then this corresponds to the case when eta goes to 0. So this differential equation is what we call the gradient flow. And throughout these slides, I will use the gradient flow to replace the gradient descent, even though that there is some deviations from the gradient flow to gradient descent. But this is to simplify the analysis, as we can use some differential equation tools from math. And there is no definition for the learning rate eta. We do not need to consider the effect of the learning rate. So okay, the first question is that, does gradient descent, or here, does the gradient flow converges? Okay, just by some simple calculus. Here we show that the convergence of the loss function value. Well, the idea is very simple, just to take the derivative of the loss function to the time t by the chain rule. We have this one. And recall that the gradient flow tells us the derivative of the parameter Wt is exactly equal to the negative gradient direction. So we can see that the derivative of loss function is less than or equal to 0. That means if the gradient is not 0, then the gradient flow dynamics, if we consider the loss function value, is always decreasing. And also we know that the loss function is always non-negative. That means for non-negative series and decreasing series, then the basic calculus tells us this series converges. It has a limit. But this limit may not be 0. Okay, it converges, but not 0. But can we say that this is a convergence for the loss function value? Can we say that the parameter converges? So here we only have Wt to some c as t go to infinity. Do we have the convergence for the parameter? The answer is not. The answer is no. This is the difference between the gradient flow and gradient descent, because for gradient descent we have some learning rate. The parameter updates from the direction of the gradient direction, and if the gradient is 0, if we hit some point with gradient 0, then gradient descent will stop. That means the parameter will converge. But this is another case for gradient flow, because there is no learning rate here. So usually this is not always true, because the parameter may oscillate forever, for example. In this example, the parameters, this is the dynamics of the parameters. And in this trajectory, all the points are with gradient to be 0. Because this is dynamics, and this is basically a solution for this differential equation. This is 0, this is 0, and this is continuous. This is differentiable. So this is one important thing that one should note. Even though that the function value converge does not imply that the parameter converges. However, if we have some restriction on the property, or if the loss function enjoying some good property, for example, the largesse in gradient equalities. These are equalities that characterize the gradient flattens around the point that is gradient 0. This is a very general condition set, meaning that every analytic function satisfies this largesse inequalities. So that means this case is very rare, because for any analytic function we have the largesse inequality, and this guarantees the convergence of the parameter. So I think we can safely say that for the loss function that we deal with in deep learning, if we use gradient flow, then also the parameter will converge. Okay, so this is the gradient flow, a limiting dynamics for gradient descent. So now you may ask, is there any analog for the stochastic gradient descent if we also treat the eta to go to 0? The answer is yes, and this is also a hot topic in deep learning, from SGD to continuous dynamics, the so-called stochastic differential equations. So basically, if you back to this SGD iterations. If you also set the eta to go to 0, then this can be approximated by some stochastic differential equations. And I will not go into the detail to describe what is a stochastic differential equation, but I will list some good references. So the first one is by Qianxiao Li, by my supervisor. He did a very nice work from and analyzed the difference between SGD iteration and the dynamics of stochastic differential equation. And the second work is by Zhiyuan Li. He analyzes the case when eta is not tends to 0, but for some finite eta. Also to analyze the difference between the SGD iterations and the stochastic differential equation dynamics. Okay, I think we can go back to the loss landscape analysis. So we know that for gradient flow or gradient descent, usually it's the case that the parameter will converge if the learning rate is set appropriately. So here we introduce the notion that stationary point means that the point has a gradient to be 0. This is called stationary point. However, even though that we have convergence guarantee for the optimization algorithm gradient descent, and we say that okay, if we stop at some stationary point with gradient to be 0, but this does not mean that this stationary point is good, because sometimes the stationary point may be very bad local minimum or some other kind of minimum. For example, in this case, if you're unlucky to get stuck into this local minimum, then this is bad because the function value is still so high. Ideally, we expected that we can use the optimization algorithm to get into this minimum. So this is the case for non-convex loss. Yes, I think maybe in the basic optimization classes, you know that for convex loss functions, all the stationary points are good enough because that all the local minima are global minimum for convex loss function. So for convex loss function, gradient descent is good enough because every stationary point is a global minimum. But in deep learning, usually we need to deal with a non-convex loss function, which is very complicated. And in that case, even though that you stop at a stationary point, this may not good. So now let's look. Let's classify the stationary points, meaning that the point that has gradient 0. So basically, there are 3 types of stationary points in high dimension: the local minimum. Here, this is the local minimum, the local maximum, and the saddle point. So the saddle point is like a saddle on the horseback. For some direction is decreasing. For some direction is the maximum. For some direction is the minimum. For this direction is the minimum. For this direction. So for these 3 types of stationary point, we know that if we look at the saddle point, this is not good, because if we're unlucky to get stuck at a saddle point, and imagine that if we put a very small ball in this saddle point, if we add some perturbation, slightly perturb the ball, then of course it will be likely to fall. That means you can still decrease the loss function value. So this is not good. What about the local minimum? Well, we cannot for the gradient-based method. For example, GDS, GD, it only uses the information of gradient. So if we are if we are stopped at a global minimum, then we stopped. Even though that we have perturbation, we are still in that region. So in that case, we expect that the local minimum is approximately approximately to be a global minimum. Okay, so here we use some mathematical tools to classify the stationary points rigorously. Here we consider the Hessian matrix of the stationary points. If this is RD, if W is in RD, then basically this is a D by D matrix. Given by the IJ's entry is given by the second derivative of the loss function. So if this Hessian matrix is positive definite, meaning that all the eigenvalues, for this Hessian matrix is symmetric matrix, real symmetric matrix, which means that it can be diagonalizable and all the eigenvalues are real number. So if this is a positive definite, meaning that all the eigenvalues are positive, then we say this is a local minimum. If this is a negative definite, means that all the eigenvalues are negative, then we say this is a local maximum. If the Hessian matrix has both positive and negative eigenvalues, then we say this is saddle point. Especially this is a strict saddle point. And here I did not list the case that when the degenerate case, when the Hessian matrix has some zero eigenvalues. This is a more complicated case, and it requires a more refined analysis. Okay, so as I said, the first order optimization algorithms only look at the gradient information. Hence, they may get stuck at saddle points. But we know that saddle point is not good because when adding some perturbations, it can still fall. So we expected that the optimization algorithms can avoid or escape the saddle points. How to do that? To achieve this goal, basically there are two ways. One is by random initialization. Another is adding some random perturbations. And now we, given that we avoid or escape the saddle points, and we will move to a local minimum. But not all the local minima are good. Only if the loss landscape has no superior local minimum, meaning that the local minimum is approximated to be a global minimum. So combining these two scenarios, we are safe to say that our optimization algorithm is good. Okay. So now let's also look into the first case, the random initialization. We first try to understand why random initialization can avoid or escape the saddle point. This is the earliest work for analyzing random initialization is by Jason Lee in 2016. I directly listed the result that he showed that under random initialization, gradient descent with small enough running rate converges to a local minimum or negative infinity almost surely. Here, almost surely means that with probability 1 over the random initialization. This is a very clean result, but sometimes not easy, not that intuitive. So to understand this result, I will use a toy example to illustrate the high-level understanding behind this result. So now let's look at the very simple case. The loss function is given by a non-convex function. you have only two parameters. This is a two-dimensional loss function. And if you calculate the Hessian matrix of all the stationary points, you can classify them into two classes. One is all the xy given by xy, x times y equals 1. This is global minimum. And for this case, the every local minimum is global minimum. This is what you can just compute the gradient, compute the hashing. But there is a saddle point in 0, 0. So we know that for this saddle point, if we plug in the value 0, 0, then the loss function is 1/2, which is not 0. So this is bad. We want to escape the saddle point. And next, I will show that with probability 1, the gradient flow corresponds to gradient descent with small enough landing rate can avoid this saddle point, meaning that the gradient flow will not hit the saddle point. Okay, let's see why is this the case. Again, we consider gradient flow. If we say we have two dynamics, xt, yt, from initialization x0 to y0. Then the gradient flow is given by just taking the derivative of L. It's given by these two. So this is a nonlinear differential equation, and there is no explicit form to express the dynamics xt, yt. So how to do that is that a simple observation is that if you take the derivative of xt squared and yt squared, for example, if you take the derivative, then here it should be times xt or 2xt. Here should be times 2yt. Let's say these two is the same, equal. Meaning that the derivative of xt squared is equal to the derivative of yt squared. What does it mean? So this means that for any t greater than or equal to 0, xt squared minus yt squared is a constant. It does not change. Okay, so now let's think about the case. When does gradient flow stop at the saddle point? When does gradient flow stop at the saddle point? Anyone? If we start from x0 to x0, y0. So hey, yeah. When does, so if we stop the gradient flow at time t, and we say when does this, if this is the saddle point, if you are unlucky to get stuck at the saddle point, that means xt is 0, yt is 0 for some t, right? But this tells us that the difference remains the same as initialization. This is what? This is 0. 0 minus 0 is 0. What about the initialization? So what does it mean? This means that this means that if we want to use the gradient flow to hit the settle point with some initialization x0, y0, then one necessary condition is that x0 square should be equal to y0 square. That means x0 should be plus or minus y0. Right? What does it look like? This is x0 equals to y0. This is x0 equals to negative y0. These two lines contain all the possible initialization that gradient flow can get stuck at the settle point. So now you see that why it is the case that gradient flow avoided settle point with probability 1. Did you see that? It's because that by random initialization, well, the key term is random. You random pick a point here, 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 here as your initialization. The probability that you are unlucky to hit this line is 0. If you randomly drop a point here into this R2 plane, it's unlikely that you hit this line because, well, intuitively, the area is 0. Or here we say the measure is 0 because these two lines has 0 measure in this R2 plane. So this simple example tells us that gradient flow avoid the settle point almost surely. Clear? So now I think maybe you have a better understanding of why random initialization helps to avoid the settle point, and why in practice in deep learning training we will use random initialization. Why? Why not just use zero initialization? Why not just use constant initialization? Well, one reason is that by random initialization we can avoid the settle point. Okay. Random initialization helps to avoid the settle point. The second ways that we introduce is that by adding some random perturbations. For example, in the settle point, if you add some perturbations, that you can still go down. This is an intuition that add some random perturbations can escape the settle point. So to formalize this intuition, we may consider so-called noisy gradient descent. This is slightly different from gradient descent. The difference is that for each iteration, we add some random perturbations, psi t. Here, the psi t is a random variable. For example, it's a Gaussian variable with mean 0 variance 1. This ensures that it will not get stuck at the settle point because you will always move a little bit. So there is a recent work that studied the convergence of the noisy gradient descent. It's by Rongge. In 2015, he showed that the NGD noisy gradient descent is able to escape settle points in polynomial time. Polynomial time means that if you want to escape the settle point, for example, if you want to escape settle, we know that settle point is that we have some positive eigenvalue and negative eigenvalue for the Hessian matrix. So usually this paper studies the so-called second order stationary point. Which is defined as if the gradient is less than epsilon, and if the lambda mean of the Hessian decision, the minimum eigenvalue has some lower bound. This is called second order stationary point. And this paper showed that the NGD is able to escape the set point in polynomial time, means that if you use the state NGD, then the number of steps or the number of iterations that is required to escape this kind of second order stationary point is some polynomial, for example, over one over epsilon. Kind of that's it. Maybe it still has another dependence on the parameter dimension D. So this is the first work that shows adding perturbations you can escape the saddle point. So now we are end up for the escaping or avoiding saddle point. These are some further readings that, as I said, that here the iterations depends on the dimension D. So to improve this result, to get some dimension-free results, there are some related works. I would recommend the papers by Jing Chi in 2019 and 2017. Yeah, this is also a good question. So originally here the people consider the noisy gradient descent. This is well, not exactly the SGD. So whether or not SGD can escape the saddle point, I mean the vanilla SGD. So this is I think this is also not completely understood, and some recent work also have focused on analyzing the convergence analysis for SGD. Because for SGD there are more terms than the NGD. For example, batch size. For example, the learning rate. So how does the batch size affect the convergence is still unknown.
This case, if like the data we get in random is like randomly matched, would that also achieve the goal that we can scale at one point?
Okay, so in that case, the initialization is a specific initialization,
Yes.
which is nearly a global minimum in your pre-trained model.
But it might be nearly global minimum in the previous one. But for
Yeah.
normalized,
Yeah, but if the pre-trained model is not so far away from your target model, then we are safely to say that the initialization of the pre-trained model can have good optimization. Yeah. Okay, so this is also, I think, also a good direction that to study the initialization of some pre-trained model, how the initialization behaves in different models. Any questions?
Is it when I run when I'm training the model in PyTorch, is it already implemented this one or not?
Is it what?
Is when I'm using PyTorch, is the default already choose random initial?
You mean the noisy gradient descent?
Yeah. Or do you know if there's
No, because you know that noisy gradient descent requires you compute the full batch of gradient, which is computation cost is very high.
But you know if there's a
But usually you can use, so for stochastic gradient descent, the gradient is also stochastic.
Yeah.
And the analysis for NGD is that this is more simpler than SGD. How can we do the random initialization? Yeah, for example, caviar initialization, timing initialization. This is the common initialization method that we use in training the deep neural network. Or you can just use some uniform initialization, Gaussian initialization, but one thing that you need to be careful is that you need to control the variance to avoid the gradient vanish or to avoid gradient exploding.
But the main thing that we choose several poles.
We should or we should not. We should choose some points
Choose several poles
to several.
instead of one pole.
Should be
Question is on which is a nice option. So just two on one to start right with that one.
What is the
Let's say that switch. You try to one with some method of initialization. You maybe try 10 times with 10 different times of initialization. So the question was that there's a different pattern that we should just like once. We try to start with multiple
do you mean that if we need to repeat the experiment for different random initialization? Yeah, you need to, for example, in practice training, you need to use some like 10 groups or 5 groups of random initialization to get an average results. Is this what you want us?
I think it's like based on what the theory explained here, like practically what's the ideal form to initialize the model and run it based on the theory that you explained. Like should you like guys use the same seed, or should you use like
I think
several seeds and take
you
the
should
average,
use several seeds.
and then
if
take
you-
the average, or
Yeah,
should you?
yeah. If you are unlucky, then maybe for one seed you get stuck at some point.
So should you just take the average of all the weights, or should you just take the average of the models that reach a certain like?
Yeah, you can take the
loss?
average.
Or should you just filter only the models that reach like the top 5, top minimum?
Yeah, you can
losses?
also take the top 5, top 10.
Yeah, but I know I can do a lot of things, but like based on the theory, what's your recommendation?
I think this is a more practical setting. Depends on what you want, actually.
Well,
Yeah.
I mean the idea is that like I want the theory to guide my model.
This theory cannot get you. This theory is just a guarantees that optimization algorithms, for example, stochastic gradient descent is good to exceed set point. But you cannot use this to get you how you train your model, how you.
Yeah. Okay.
It's just this just provides a theoretical understanding on the advantages of the optimization algorithm. Okay.
Just now, all the analysis is based on gradient descent match. Like, will the result only action also applicable?
Yeah, this is a question that Sophie asked. So yeah, there are some recent works that analyze the vanilla SGD, but it's still not completely understood. So to study the reason to study the gradient descent is that there is no batch size, so we do not need to consider the effect of the batch size. But once you add some additional hyperparameters such as high batch size, then the problem becomes complicated. Okay, now let's move to the geometrical property of the loss landscape. So now following the land, then we are able to escape the saddle point efficiently, but now we go down to finally we stop at some local minimum. Ideally, we expect that the local minimum is approximately a global minimum. But usually this is not true, especially in some deep learning models. The loss landscape can be complicated. But there are some works that study the local minimum property. So even though for non-convex problems, there exists one neural network architecture that the loss function, for this loss function, the local minimum is every global minimum. This work was due to Kenji Kawaguchi. So he considered the linear neural network models, deep linear neural network models given by this form. X is the input, W1 is a parameter for the first hidden layer, WH-1 is this is a H layer linear neural network. And if we consider the linear neural network means the activation is linear. Otherwise, there should be some activation phi. If phi is just an identity map, then this is called a linear neural network. So for nonlinear, that means, for example, ReLU. After this operation, there will be some ReLU.
If we don't have a non-linear acceleration function, isn't that?
Yeah, then this is a linear. Yeah. Because you can treat it as an identity map. Then this is the linear neural network. Do you want to ask if this is equivalent to just put one?
Yes.
Okay, I think this is a big misunderstanding. Actually, so this architecture, for this example, if you want to optimize this loss function, you have some dynamics from WH to W, or we can just use the example before, this one. You cannot say this is equal to x minus 1 squared. This is a non-convex, but if you combine all the parameters into the same, then this is convex. But the optimization is different. There are two parameters.
Linear neural network, where is the non-linearity, and over here is the square of the magnitude, some sort of a non-linear function. But I didn't understand that a linear neural network, what is the part that makes it non-linear? Because if it's not non-linear, then you just do all the methods, multiplications with the single methods, multiplication, and then linear transformation.
Yeah, as I said, even though this, well, you can, because now we are optimizing a function. So if you think about x, y times y to use a single parameter x, then this is a convex function. But that the optimization process are different because there are two parameters and the optimization.
What you really understand is the loss function is the non, it's like a non-linear loss function. But I was asking, like, in that other slide, it's a linear neural network. What I didn't understand is, like, how is the linear
This is
different from just the one layer linear regression almost? Yeah, as in over here, the WH into WH minus 1 up to 1. Isn't it? As in, can't we do all of these multiplications and replace that with a single linear? So eventually just have something that WX is equal to 1.
yeah, you can do this, but optimization are different. You can imagine that if we want to optimize this loss function compared to optimize Wx minus y squared, this is a linear regression, right? But the thing is that in the optimization process, we are given an initialization. Even though that, okay, if suppose that we are from the zero initialization, and if we do a gradient descent, the results are different. Because the optimization for the gradient descent for each parameter interacts with each other. But if you treat this as one parameter, there's no other.
I think the part that struggling with is we can replace between WH minus 1 with some other variable, let's say matrix A into matrix B into matrix C. It's just a sequence of matrix multiplications, right?
Yeah.
Inside a square.
Yeah.
So since it's just a linear transformation, like matrix A into matrix B into matrix C, isn't all of that basically the same as one final matrix that you get after multiplying all of them?
How to say that?
As in, like, is there any point of adding more than one layer? So basically, no layer. You don't have a non-linear.
If you don't have nonlinear, yeah, this is the case that you don't have.
Yes. I guess I can ask you after.
Okay. So for this neural network models, if we want to optimize via the squared loss, this is a non-convex loss if the layer is greater than or equal to 2. And here Wi is some matrix X is input, Y is the label. And then in this paper, they proved that very simple with very straightforward, a very clear result. If X and Y have full row rank, means that the rank is equal to the number of rows. Then all the local minimum of LW are global minimum. So that means this loss function looks like, well, maybe it looks like this. And all the local minimum are on the same level set. Maybe this is the case for the deep linear neural network models.
I think the result is very simple.
Yeah, but the proof is not that trivial.
Yeah, I know.
If you are interested, you can. Yeah, this paper. So Kenji also have some works on the neural networks that global minimum, that some neural networks has no superior local minimum. I did not check the proof. Oh, I forgot the details of the proof, but the result is very.
I have a question. What's the derivative of the for this X is a P by N matrix, so the rho is that its feature, right?
Yeah. Each row, each column is a feature.
Each column is oh yeah,
I think it's a sample size. Yeah, so means that the dimension of feature should not greater than the number of sample.
feature independent or data independent. This means all the features should be independent for all the data points.
Independent work, there is no.
In case you have
Oh, then they're independent rows.
Yeah.
Yeah.
independent features. It's weird.
Yeah, this is not like the, for example, linear regression. If you consider underdetermined, then the n should be less than d0, right? The sample size should not be greater than the number of features. But in that case, the full row range means that this is like overdetermined case. The sample size should be larger than the feature dimension. Oh, I think maybe here is a typo. It's not actually not be full row rank, should be full column rank. Otherwise there is only one global minimum. Right. Okay, maybe I need to check the statement. Okay. Okay, so now for nonlinear neural networks, they can have much more complicated landscapes. So here I also provide some related works on nonlinear neural networks that study the non-superior local minimum. Okay, I think we can go to the last part before we having lunch. Okay, so this is the implicit bias part. This is implicit bias is actually answers the question, does the minimum have small population rates? So the answer is that sometimes yes. And this is observed by some previous work that for some optimization algorithm GD or SGD, this is implicitly biased towards a simple solution. To have a high level understanding of the implicit bias and why the minimum have small population risk. Here I use the example in classification problem. So here, given that we have two classes, the flat one, the wet one. Now, if we want to use the hyperplan to classify these two groups, here we are given three hyperplans. classifiers. Which one do you think is the best? H3, because it has largest margin, meaning that it is compared to these two classifiers, H3 is more robust to all the generalization can be better, can be the best compared to H1 and H2, right? So this case, so here the implicit bias, we can see the optimization algorithms is implicit bias towards the simple solution. Here the simple means that, for example, for classification problem, the margin is large. That means if GD or SGD for the classification problem, if this optimization algorithm can converge to some margin maximization direction, then we can safely say that GD and the minimum obtained by GD SGD have small population weights because the margin is maximized. So to understand the implicit bias of gradient descent, here I also use a toy example here. Suppose that we have 2 points. The green one is -1. The blue one is 1. And we want to classify these two, separate these two by a length. Start from across to 0. This is given by y equal to wx. So as you can see, any line y equal to wx can classify these two points, right? But which one is the best? Is it y equal to 0? Or x equal to 0? Yeah, x equal to 0. Because the margin, the margin is defined the distance between the hyperparameter to the data set. Margin is the largest. So now let's use the logistic regression to classify these 2 points with this linear model. Let's formalize this statement. So here our decision boundary is given by the sign function of this linear classifier. If this is for given w, if this is positive, then we say this belongs to this class. Otherwise, this belongs to the green class. And now we can assign the probability to these two classes. For example, given x, the probability that the class y equal to 1 is given by this logis, also the sigmoid function. And and also you can compute the probability that this is assigned to be y equals to 0. The probability that this is on -1 is given by 1 minus this probability. Okay, so now we have the probability. Now we can do the logistic regression. So how to do that? We have the probability. This is the probability is given by, and also we write down if we say the label is 0, 1, this is 1 over wx. Right, for this binary classification problem, is suppose we are doing maximum likelihood estimator. Now we compute the log likelihood. So this is given by the product to the power 1. Suppose that the label are Bernoulli distribution times, this is a log, so we have log y equal to 0, given x to the power 0. Right, and if we take, then this is just a 1, if we take the log, then the negative, we want to maximize the log likelihood. So now we minimize the negative log likelihood. We say NL. Then just like take a negative. This is given by negative log 1 over. This is a negative log likelihood function. Well, then this is just equal to log 1 plus e to the minus wx. So here we get the logistic regression on these 2 points, the logistic loss function. And now the problem is that we want to minimize the negative log likelihood on these 2 data points, negative one and positive 1. Well, this is a very simple loss function. It decreases to 0 when w equals to infinity. That means the global minima, if we denote it by w star, then w star is positive infinity. And if we use the GD to train this model, if there is no regularization, then GD will diverge to infinity because it's a function, decreasing function. So in some, I think maybe in your deep learning lecture, maybe you are told that to avoid some overfitting, especially for the logistic regression, to avoid this divergence of gradient descent, you have to add some L2 regularization or some other types of regularization to avoid that the gradient descent diverges. But it is the case that adding the regularization, you avoid overfitting. Or we can look at the case. W is in positive infinity. What does the decision boundary look like? If W is infinity, this is like the y-axis, right? If W is infinity. So that means, in that case, even if we use gradient descent and without regularization, we can still, the gradient descent can still maximize the margin, can converge to the margin maximization direction. So basically speaking, for the linear separable data set, gradient descent, if you do the logistic regression, it's not the parameter value determines the generalization, but it's the direction of the parameter, the normalized vector. This determines the direction of the classifier of the margin or of the classifier. So you can see that for some simple case, adding regularization will not prevent, but will be worse than not adding regularization. So this is what we call the implicit bias of a given optimization algorithm. That is, even though without the regularization, the optimization algorithm is implicit bias towards the simple solution. So this example reveals an interplay between the optimization and regularization via the implicit bias. And also this work by Daniel Sorge in 2018, he showed that for classification problems or linear separable data, that means, for example, for binary classification, the two groups data can be separated by a linear function. Then if we use GD, gradient descent, to train on this linear separable data with cross entropy loss, the interesting result is that even though we do not have regularization, gradient descent is implicit bias towards the margin maximization direction. You do not need regularization. And this in turn inspires many other works handling other types of data, because this work, the earliest work considered linear separable data, but usually in practice, the data is not linear separable. It's very complicated, maybe neural network separable, nonlinear separable data, and also other types of architecture networks. So this is the linear logistic regression with linear model. And other works also work with some networks, for example, the neural networks, deep neural, shallow neural networks, and other kind of losses. So here I list some interesting references. Okay, I think this is the end of the morning session. And this is the end of the optimization part. So maybe after we having lunch, if you are still interested in the generalization part, which will be a bit math heavy. This generalization part studies so now optimization is good. Okay, we are given a learned model, but we still don't know how does the learned model perform on unseen data, on test data. So this is related with the generalization. And we will give some generalization analysis for the learned model. Okay. Thank you. Maybe we can have lunch. And maybe we can go back 1 hour later. Huh? 4:30，4:30，有人开始吗？
吃饭了，还没开始，
还没开始。
没准备。
我还想说把这个分在下午。
行，休息啊，休息啊。几点？1点半。
Okay,
1:30。
Yeah, 1:30.
1:30.
We come back to continue the generalization.
But the lunch should be ready in about 15 minutes. So maybe all of you can go to level 2.
Okay.
Have a tea chat, anything.
How long after lunch do you think you need?
Not sure.
How many slides do you have?
About half. So if you only finish half.
Okay. And the second is
About the linear neural networks, like
Yeah, you can write down.
Yeah, I can
what you want.
so I think
chain of metrics is just illustration, analyzing optimization, so analyzing optimization dynamics. But in fact, if you are really want to optimize the linear case, you can just write down them as the one matrix. If you are really doing the optimization.
The optimization are different. Because well, one example is that if you just use one matrix, this is not that representative as one single matrix, because the product of the matrix you have some rank constraint. So okay, given any, you cannot say that given any matrix you can represent the matrix with the series product of this kind of matrix. You cannot do that. If we are given the D0, di minus 1. Otherwise, this is like the matrix decomposition. Yeah, so this is
so for any matrix you cannot do decomposition, right?
You cannot guarantee to decompose this exactly.
Some sort of moving matrix, maybe apply some non-linearity was there. Then that output is multiplied with the weight matrix of that layer, another non-linearity, so on, right? So from what I understood in linear neural network is something like this. You have
Correct. Some matrix.
Matrices multiplied. So my question is, when you have these weight matrices without non-linearity, isn't this the same thing as some matrix?
No.
Why?
Okay, the case is that
all the matrix multiplication is going to give
actually
you
no.
some matrix.
Yeah, because okay, I will say this one is more representative than this one. I will show you why.
More
Representative.
what does that mean?
Okay. That means there exists some W star.
Okay.
Such that you cannot find A, B, C if we say the shape is already fixed, for example. Yes, such that ABC is equal to W star. This is the matrix decomposition talk.
Yeah, but it is, as in, like, if you're going to be multiplying all of the matrices, this will always exist.
Okay, so now let's look at another thing. If we want to minimize over A, B, C, this is a problem. And if we want to minimize W, you think these two problems are the same? Are equivalent?
No, my point wasn't about that. My point was, when you can write all of these the matrix multiplications, and you can do all of this with a single matrix, then isn't a linear neural network nothing other than just like a single linear model?
No.
Why not? Isn't that why? Why having a non-linear activation is important in the neural network?
Oh, no.
Otherwise, all of the matrix multiplications can be done.
Okay,
just a
so
single one.
okay, so for your question, the reason that we have nonlinear is to make the neural network more representative. Because if you only use linear, then the sum of the labels, this cannot be zero sometimes. But if you add some nonlinear, then this is like underdetermined question. So given some input and label, it's more possible that you can achieve zero loss. This is the reason that why we use nonlinear. because for this problem, okay, if just think about the case that if A we say is a row vector, and we say B is a column vector.
Yeah.
B is a row vector. And if we want to minimize AB minus some y is n by n, you cannot go to 0. Because the rank of AB is 1. However, the rank of y can be n. This is arbitrary given. That means this is not representative. And this is the matrix decomposition topic.
So what I meant was like, once you do this A into B, that will give you an n cross n matrix, right?
Yeah.
Which is what I am saying is this matrix. So this is equivalent to, or exactly the same as W minus Y. As in like, however we want to frame an optimization problem. These two are exactly the same, where W is A into B.
Is a type of A times B.
Yeah.
I agree.
So that's what I meant in a over here, in like a linear neural network. When there's no non-linearity, isn't all of this
okay.
just one?
Okay, then you can change the notation here, use the big W, and here W is like the form WH times WH.
Sorry, what I meant was all of this part can be instead be just one single matrix, right? Once you do all of these matrix multiplications, you'll get some matrix at the end. So isn't this exactly the same as just one matrix into X?
No, right?
Yeah,
Because,
only if the matrix can be expressed as the W.
yeah, because it's not always the case, because this example shows that A is rank 1, B is rank 1. But if you cannot simply like given any W, you can have this result, because W can be rank N.
Yeah.
It's way better representative than
I
AB.
didn't say it's any W. I said once you do all of these matrix multiplications, only that particular matrix. Like
if matrix multiplication, you can get matrix multiplication from like n matrix into one, right?
Yeah.
Exactly. That's the basic math. But if you are doing optimization, it's different because you need to care about the rank.
that's why I've tried to clear at the beginning. I'm not talking about the optimization at all. I'm just trying to understand what is the point of a linear neural network, because all of this portion, after you try to multiply WH up to W1, you'll get one final matrix at the end, right?
Yeah.
Let's call that W whatever star. After you all those multiplications, you get this. Multiplying this with the input.
Yeah.
So isn't a linear neural network just one layer of?
I don't think so.
Why? Because at the first stage, you have W1 into X, so that's your first layer, right? And then you do W2 into the output of W1 into X. That's how you will be doing your matrix multiplications here.
I think let's consider an example. Consider the multi-layer perceptron neural network.
Yeah.
That is exactly the metric multiplication, right?
Yeah.
So, like, if what's the difference between like three-layer MLP with one-layer MLP, but the parameters like the one-layer MLP is like larger it's the how should I say, like
The exact weights may be different. I'm not saying the weights will be the same, but if you don't have some sort of a non-linearity
yeah,
in
let's
your
not consider.
sorry.
Let's not ignore the non-linear part.
Yeah, which is why I asked, like, what is the point of a linear neural network? Because there is no non-linearity here. So
Can you use the example like I listed for x, y minus 1 square? Let's simplify this case.
I'm
Can
not even
I try and rephrase your question?
sure.
So let's say you have a neural network of this linear neural network and you optimize the weights. Do you necessarily have to take x times w1, then multiply by the next layer and so on? Or can you just multiply all of the weights first and then multiply it by the inputs? Is that what it's asking?
Sort of, like what I meant was this basically shows that you have h different layers, right? H different layers and there is no non-linearity in any of the layers. So if you don't have a non-linearity, using the properties of linear transformation, once you multiply all of these matrices, then it doesn't really matter whether you have one layer or 100 layers or 1000
So
layers.
you multiply all of this first.
Yeah, and you get a single layer.
Yeah.
So, what is a neural network? If you don't have a non-linearity, it's just a linear model, right? It's not a linear neural network.
Yeah, this is what I think I have expanded your question from two sides. One is that even though that you express that this one is only one single matrix, you cannot guarantee that for any single matrix you can express this matrix as a product of different matrices, as this example shows.
Yeah, but I'm saying I don't need to do any of that, right?
Yeah, and another thing is on the optimization or on the problem. If you, the first problem is that you want to minimize the loss function.
Yeah, that's exactly.
Yeah, but I think these are the two important things that you cannot treat this one as the same as only use one single matrix to get a linear regression. Yeah, this is my answer.
All right, please.
Let's discuss the.
Yeah, surely you can discuss.
I wanted to ask something else.
So you have some.
Yeah, I wanted to ask. It's about implicit bias.
Okay.
Actually, I'm not familiar with it, and I don't understand like what kind of bias is implicit bias, because you said that when you have an implicit bias, then regularization doesn't work. Right? So, but what if you have an explicit bias? So, like for example, you explicitly.
Well, explicit bias means that you have some regularization. Because the regularization
means the explicit regularization will fail, but means you already have equipment with implicit regularization already.
So if, for example, I have some knowledge of the system that I want to model, and then I place that in my loss function, that's also a form of regularization.
Yes.
But then in that case, the regularization would be
this is called explicit bias.
okay.
Yeah, the implicit means that you do not have any regularization, you just use gradient descent. Then it's inherently implicit bias towards some good solution.
They're just going to improve interesting phenomenon while you training your neural network. The optimization algorithms will converge to well. Yeah.
Oh, okay.
Something like that.
Okay. Yeah, that's all. Can you share the slides
Sure.
with?
Sure.
Okay. You want to share now, or maybe I can share after this?
Yeah, after the thing, I gotta go for another meeting later on. So like,
Okay. So
I
how
won't be
can I
able to
share?
attend the second half. But like, you have the name list from. Do you have the name list of people who attend in real life?
No, I think maybe Sam has, but I do not have.
Oh, okay. Then can
So
I
what's your
give you
email?
My email. ZIYU. C Why? Right. Yeah.
Okay.
Thank you.
So you are working with?
I'm actually from computer science. I have
Computer
the
science.
same supervisor as Guillaume.
At school.
Guillaume, the European.
Okay.
Guillaume.
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 Okay.
Yeah, we have the same supervisor. Our supervisor is French, so Guillaume's name has been butchered.
Okay.
Guillaume, according to the French supervisor.
Oh.
I think the correct pronunciation is Guillaume.
Guillaume.
Yeah, we cannot pronounce it.
Yeah, I can't remember. Yeah.
Too hard.
Yeah.
So you are not doing the deep learning theory things?
I'm doing small physics in form.
Nobody except you.
So not really deep learning.
Okay. Okay.
Yeah.
So now do you have the better understanding on
But
the
this
deep
is,
learning?
this is so mathematical. It's very unlike what I do.
Oh, you think this is so mathematical?
Yeah.
Okay.
Yeah, I think like the slides are sometimes a bit confusing because it's not clear what the point of every single slide is. Like I think maybe a good practice would be to have like a headline on every single slide because a lot of your slides have the same titles. So you don't know what the point of every single slide is. Yeah.
Okay.
Thank you.
How do you think the? Oh, are you clear?
It's interesting. Don't know how to say it properly. The first one is about
No. Yeah.
with this type of Fourier transform. I mean the Fourier.
No, it's very.
Yeah, this I think. Yeah, yeah. I think this one is interesting.
Oh, do you think this one is interesting?
Yeah. Because I have seen many works applying Fourier transform neural network.
Okay.
Yeah. But I'm not sure what do you mean by infinite width network?
M should go to infinity.
Yeah.
M is the width.
Does it mean that it has better expressivity than basic neural network?
No.
No.
No, because we can also express because this requires the function to be L1 integrable.
Yeah. So it must be A1. It's
Yeah.
like
Not Lipschitz, L1 integrable, meaning that the
yeah.
absolute value is integrable.
I to show yes.
But usually this is a very strong condition.
Strong, yeah. But this
So-
is continuous, right? And this is for the basic loop.
So continuous is not enough. You need this to be integrable. Otherwise, this will be blow up.
Yes. Do you know some work that instead of uses self attention, it uses Fourier attention. I'm not sure if it disconnects the
Maybe you can search the work by Eric Price
error
in UT Austin.
Justin.
Yeah.
Where that's Eric Price.
Maybe not this name. Oh yeah,
Eric Price.
this guy.
Yeah.
He has some paper on the Fourier FFT.
I see.
You can have a look at.
So
How
the
many
work
people are online?
Only
Maybe tell them
only 3.
that you're supposed to come back.
so this is your research.
Only one. No, nobody's online.
Huh?
Nobody's online.
Who?
Nobody's online.
Oh, 3 people. Are
No, Sam, the computer who's recording,
Gladys.
Linus, but she's not. She's admin.
Okay, yeah. This is where my research focuses on very small topic.
Are you
It's not
gonna
a-
present your
Wait,
your
that's my
research?
work?
You're gonna present your work?
I think I do not have time to present.
Oh, but is it in the slides?
No, it's not in the slide.
Okay.
But what's the specific way? What is it about?
It's about the interplay of optimization and generalization. So
Right.
basically, in the generalization, I will introduce some tools to bound the generalization gap. And you will see, so the bound sometimes based on some parameter space, like norm-constrained parameter space. So my work focuses on how to improve this bound. So like I want to connect optimization and generalization.
Can you tell us when you connect when you talking about
Okay.
oh, like when you were saying, like, I was a bit confused about this part here, like sorry. So here you said if this approaches 0,
Eta equals to 0.
yeah, like, so the derivative is equal to 0. So the ODE can have oscillating solution.
Yeah, you can.
How? Like, because the weight is not changing over time.
Yeah, just like the example oscillating all the in this trajectory, all the points are stationary point. So this is differentiable trajectory satisfy this.
Can be equal to 0.
No, exactly equal.
Yeah.
Then
The derivative,
satisfy this.
like,
ODE.
if this is equal to a constant, then it's growing, or
Yeah, then
equal
we'll
to
decrease
0, it can be oscillating.
Yeah.
I don't remember very well. Like, I remember last year I studied that, but
Okay.
differential equations, but I don't.
But sometimes this is
But if you say so.
the oscillation only happens for some wheeled function. Because for analytic function.
No, because just intuitively, the weight doesn't change. How
Yeah.
can it change?
Yeah, this is you should not think this as the gradient descent.
No, just this. If this is equal to 0, EWT.
Yeah, so the case is very strange, And there is a curve.
Yeah.
On this curve, all the points are stationary points. All the points have 0 gradient.
It means local optimal.
Oh, okay. Okay.
If it goes 0, we stop there.
But for gradient flow, you may not stop.
But in most cases, if you do it randomly enough, you will not stop.
Yeah.
One more. What is the difference between radiant flow and radiant? And do not catch.
This two are equivalent only when eta goes to 0. But in practice, eta is not 0. So there are some deviations.
So radiant flow is radiant in practice.
Yeah. In practice, you cannot, the gradient flow is unrealistic because you cannot achieve this by setting eta to b.
Well, of course, theta is the learning range. So
yeah.
Yeah, sure.
我可以帮我问一下谁的手机丢了？我被扫描。
在哪里啊？
在楼上，就是坐在我们那桌在靠这边的位置。
谁的手机丢了 ？Whose phone is lost? Shall we start? Hmm? Okay, so before we start, maybe I think I should have a quick recap. What we talked in the morning. Okay, so in the morning we talked about the two parts of the deep learning theory, the approximation part and the optimization part. So we know that neural network is a universal approximator. It can approximate any continuous function, and then by using some optimization algorithm, we can get a optimal model in the observed data, training data. So now the problem is that whether or not the learned model generalized well on unseen data. So the question related with the population risk and the empirical risk, the gap. So the purpose of the generalization part is to bound the gap between the training error and the test error. So as we said, this is empirical risk, also the training error on the training data set xi, yi. And this is the usually called the test error. Also the population risk given by taking the expectation over the data distribution D. So usually the data distribution D is unknown and we don't know what this exactly. But we have the law of natural number in probability. That is for any fixed W. So this is the function with respect to the parameter W. For any fixed W, the law of large number tells us that if n goes to infinity, then this summation can approximate this expectation. If n goes to infinity. So this is an asymptotic result, but we don't know the non-asymptotic result. So given a finite sample size n, how close can the empirical risk approximate the expected loss? We don't know. So here we need some tools or concentration inequalities. And next I will start the concentration of a random measure. So to obtain the non-asymptotic results for finite sample size n, we need concentration inequalities which provide bounds on how a random variable deviates from some value. For example, is expected value. For example, if x is a random variable, and suppose we know the distribution is a standard Gaussian, then the probability density function looks like this, right? So what if can we have some bound or some probability bound on what's the probability for x in lies on this area, like -1 to 1? So then you can compute the area of this side, and then you will know what's the probability that if I randomly draw a number from the standard normal distribution, then with what probability I can guarantee that this is in -1 to 1. So this is the what the concentration inequalities tell us. For example, for independent random variables z1, z2 to zn, and given a certain functions, the concentration inequality study how does this function concentrates around its expectation. For example, we can take the function to be the average of the random variables. Then this returns to the large law of number. When n goes to infinity, we know that the average converges with probability to its expectation. Okay, now let's introduce a powerful tool to bound the deviations from a random variable to its expected value. This is called McDiarmid inequalities. So this inequality shows that if the function f does not change too much when only one of its n arguments is changed, then f concentrates well. Okay, maybe I should directly show the theorem. Maybe I should give some intuitions on this theorem. So now we want to know the deviation from the empirical average with the expectation of x. Suppose x1 to xn IID, for example, uniform distribution. So intuitively, if we the law of not large numbers, tell us if n goes to infinity, the mean of the sample mean converges to the expectation, which is 0. And now these McDiarmid inequalities tell us if the sample mean, this is the function f here, satisfies the bounded difference condition, which means that if we change only one argument, for example, this is the original one. If we change it to, if we only change the first one to x1 tutor, here x1 tutor is also a random variable, uniform, satisfies the uniform distribution. So this inequality tells us that if this quantity is close to the original one, just replace one random variable with another copy. If this two value does not change so much, then we conclude that this deviation is small. So this is like the local change is very small, then the global change can be controlled by the local change. So in this case, the difference between these two values is given by x1 minus x1 tutor over n. If x is a uniform distribution, which is a bounded random variable, then this is bounded by 2 over n. So we can see that if n is very large, then the change, the local change, if we only change one argument, then the global change will be no greater than 2 over n. If n is very large, then this is very small. And this inequality also gives an explicit probability. That is, with probability at most this one, the deviation is at most epsilon, with any epsilon greater than 0. So now let's let the delta to be the failure probability. And we suppose that each CI is 1 over n. This corresponds to the uniform distribution case. Now let's see what the failure probability is. This is exactly over 1 over n. And now we use the delta to represent each epsilon. Then epsilon equals to this form, right? And then we can say that with probability, at least 1 minus delta, we have the deviation is less than epsilon, this one. So this is a non-asymptotic result that the McDiarmid inequality can tell us. That is, if we, for example, we fit delta to be the failure probability to be 0.1, then we can see with probability at least 90% over the random choice of the random variable z1 to zn, the deviation will be log 20 over 2n. And if n goes to infinity, then deviation goes to 0. That means the sample mean can converges to its expected value. Clear? Okay, now let's look at what results can we get by using the McDiarmid inequality. One application is to use the McDiarmid inequality to deduce the well-known Hofstad's inequality on bounded random variables. So just as I showed here.
Looks like
kind of, but Chebyshev inequality is that. Okay, let me write down. But I don't know how to spell it.
He has a Y there, Chebyshev.
Yeah.
After the B.
if I have
Chebyshev inequality. Okay, I'm not sure if I remember correctly. The Chebyshev inequality says that. What does it say?
Can Google it.
For any non-negative
Relationship between the expectation and the variance.
for any non-negative random variable x, we have what? The probability that x is greater than or equal to
The probability that the x minus expectation is more than k times the variance. Understand it? Then
okay, never mind. But this Chebyshev inequality is a concentration equality for one random variable, for single random variables, and you can use the Chebyshev inequality to deduce the Hofstad's equality.
I mean, is it tied about
Okay, this is a good question. So, you know that for Chebyshev inequality, the requirement is that the variance is finite, should be finite. There is an upper bound for the, so for some case, if the, I think for some cases, the Hofstad's inequality is tighter than Chebyshev inequality. Because you can think about an example. X is a standard Gaussian. So this tells the Hofstad's inequalities tells us that Px, the absolute value, is smaller than some exponential decay term. That means the standard normal distribution has some exponential decay tail. Right? The probability is exponentially decay. This is what the Hofstad's inequality tells us, but what does the Chebyshev inequality tell us?
the random variable to be but between A and
Oh, okay. Actually, this can be relaxed to some sub-Gaussian random variable. So I just read it as a simple version. So it states that it should have an exponential tail but the Chebyshev inequality tells us the tail is scalar at 1 over square root d. Oh, no. 1 over t squared.
Polynomial.
Variance. Is it minus ex? Maybe like this. So that means the bound that the Chebyshev inequality can obtain is like polynomial decrease, which is lower than the exponential decrease. So in that case, the Hofding is better than Chebyshev inequality. Okay. Well, the proof is straightforward. Just let's just use the McDiarmid with f equals to the sample mean, and then verifies that f satisfies the boundary difference condition. If we only change one argument, then the function value will change within bi minus ai over n. And then plug into the McDiarmid inequality, we can get the Hofding. Okay, so now I will let's see an application for the Hofding's inequality on some deep learning models. How we can use it. So recall that we want to bound the gap, the generalization gap, by some population risk. The test error minus the training error. Here we use Ln to denote the training error with n data set, and we use Ld to represent the test error with respect to the data distribution D. And now we consider an example with 0,1 loss, meaning that the small L is given by indicator function. If the output y is exactly equals to the label y hat, then this is 1. Otherwise, this is 0. So literally, the 0,1 loss returns the misclassification rate on the data distribution D. We just count the number. If this classified correctly, then this is 0. Otherwise, this is 1. Okay, so here let me write down the population risk. This is expectation. And we want to bound the gap. So note that this is expectation over the loss function. So to use the Hofding's concentration inequality, we just take it out. This is expectation. Then the random variable becomes this one. This is the loss function for the first sample. Then we have n random variables, and usually we will assume that the data is independent. Then by some continuous transformation, we can say these n random variables are independent. And also, this one is bounded. from 0 to 1. So now we can directly apply the Hopkins inequalities with AI to be 0 and BI to be 1, and we can get a non-asymptotic result for the 0-1 loss for the generalization gap with respect to the 0-1 loss. So I just copy the result here for any fixed classifier. This is a parametric classifier given by Fw. Then the probability with the deviation of the gap greater than or equal to epsilon is given by is no greater than this probability. And also by doing some transformation, just to let the failure probability to be simplified as delta, we can solve the deviation epsilon. And now we can see that for any fixed classifier and any failure probability delta, we have with probability at least 1 minus delta over the random choice of the independent training data, for example, with size n. This is the test. This is the training error. And only there is another statistical error term given by square root. Square root is of the order 1 over square root n. So this proposition tells us that, so imagine that we have a fixed classifier such that this term, the training error is 0. That means this classifier can 100% classify all the data points, all the training data. Then if we increase n, so we can see that the test error can also be 0. I have a question.
How do you get rid of the observability?
Okay, so basically the absolute, like for example, if you consider the difference as a whole random variable, this has mean 0. Now you can take expectation. So this is like
this is the metric.
Yeah, symmetric. Yeah. So if the absolute value is greater than to epsilon, means that you have 2 sides, just to divide by 2. But here I do not use this. So because if the absolute value is less than or equal to epsilon, we can deduce that a minus b absolute value is less than. If epsilon, we can deduce this one. Okay. Okay. So if a minus b less than epsilon, what we can say? Can we say a minus b? We can use the upper one to deduce the bottom one. And I just ignore this side. This is what this.
But you can also write the first line.
Yeah, then you can then there is another term greater than or equal to negative training loss plus. But usually this is not what we want, because we already know that the probability should be greater than 0. So no need to rather than another negative number.
Because A and B are symmetric, right?
Yeah.
So you can just
Yeah, if you use the symmetric probability, then this becomes a 1. But I do not use it. I think the order is the same. Okay. But you okay, so here the one thing that you should know that here the proposition holds only for fixed classifier. What's the problem for the fixed classifier? Can we use this proposition to say that the only thing that we need to get a good generalization performance is to increase the size, sample size? Can we say that? We can, the answer is no. It's because that this classifier is fixed. But in practice, when we train it, the learned model depends on how we choose the training data. So basically, this one should depend on the training data. But here, the proposition is only for fixed classifier. So for example, if I have a fixed classifier, this classifier fits well on one specific data set, training data. For example, if the classifier fits on this data set, that means the the accuracy is 100%. And now let's consider another data set, xi tutor, yi tutor. If we still use this classifier, it's possible that the accuracy will be 0%. I mean the chain. There is no chain. This is a fixed. So it's possible that this classifier only fits well in this data set, but does not fit well on another data set. Yeah. Sorry? Yeah, independent. I just randomly draw another data set because we have a distribution data distribution. Right? So this is a problem that we do not want the classifier to be fixed. What do we want? I think ideally what we want is that we do not have a fixed classifier. The statement is like for any failure probability with high probability over the training data, an algorithm can return a classifier such that this holds. So this is what we want. You see the difference? This is fixed classifier, but we want for different training data, the optimization algorithm can output a classifier that has good generalization. Okay. So basically, this proposition does not answer the question that why an optimization algorithm generalizes well, because this proposition requires a fixed classifier.
Are you saying that the W there is when you say fixed, is the W that is fixed?
Yeah, means that W is fixed because this is a parametric function. And here the one desired statement is that for a given optimization algorithm A with high probability, A returns a predictor that has a small test error. So this is what we want. And if this statement holds, then we can say the optimization algorithm A is good because the test error is small.
But like there's a theorem called no free lunch theorem. Like it doesn't have any relationship with this topic.
So because here we say that with high probability, but no free lunch says that if this algorithm fits, there is no algorithm can handle all the cases. But here this is probably approximately the pack learning framework.
So if we remove the high probability, then it's allowed.
Yeah, then it's so how do we fix this issue? How can we measure the generalization ability with when you are given an optimization algorithm? So one idea is to consider the worst case generalization gap of all the possible predictors F the given algorithm may at output. So this is given by the Schiff-Riemann or the maximum generalization gap for all the possible predictors F. If this Schiff-Riemann is very small, then we can say the algorithm A is good because the worst case is small. So the idea of uniform deviations is that even though that output predictor depends on data, we eliminated the independence issue by bounding the generalization gap on all the elements of F before we see the algorithm output. And this is also called the uniform deviations. We consider the deviation around uniformly of all the possible choices of an algorithm net output. Okay. Okay, so now our task becomes how to bound this term. Can we have can we have some tools to bound these uniform deviations? A straightforward, a very simple example is that the case that when F has only one element, then this reduces to the formal example. Then the F is a fixed because we have only one choice. All the algorithm only output one classifier. Then we can use a Hopf. But what if the function class is finite? Say we have k possible output for the algorithm A. Let's say if an optimization algorithm A outputs a finite function class with parameter W1 to Wk, then we can also apply the Hopf's inequalities just by taking some union probability bound. How to do that? For each j, for each function class, there is one choice. For each function class, we have a concentration inequalities. And then we take the union bounds over the events that the deviation is greater than or equal to epsilon. So if I write it down, if we have, say, the following events, one, then the probability union bound tells us that the probability that either one of these events happen should less than this all the probabilities if we sum all the probabilities. So this means that at least one event happens. So now we can just use to take a union of all these events, and then we can bound the probability that at least one function class has very bad deviation. So the idea is that we just take this term to be delta over k, and then we solve the deviation epsilon. Then taking a union bound across all the possible function class, then we can say with probability at least one minus delta, the deviation, the gap is no greater than this term. So since k is finite, k is a finite number, and also if n is goes to infinity, this term will vanish. So that means the Hofstadter inequalities guarantees that if an optimization algorithm only outputs a finite function class, we can increase the sample size to get a good generalization. But in practice, the case that the function class is infinite. For example, if you use gradient descent and you use some random initialization, we have infinity number of function class. The learned model means that the k should here k is infinity. Then we cannot directly apply this result. As you can see, if k is infinity, then this bound becomes non-vacuous, or becomes vacuous, because then the upper bound is infinity. Then this input does not tell anything. So now the problem is, it becomes that how do we handle the infinity class function class?
So if we increase the size of n to, let's say, to the infinity, so the terms on the right hand side will all be 0 if we assume that f learns with.
Yeah. Then this is
so the generalization error will be small, very small.
Yeah.
Can we say like so just want to do some connection to the previous part of optimization. Can we say that it reaches the global minimum approximation? Can we say that?
You need to specify the global minimum of what? Global minimum of the population.
Yes, please.
Yeah, if this is 0, then this is global minimum. if n goes to infinity.
So you can say
But you need n goes to infinity. You see, sometimes n is infinite. Then you cannot say this is the global minimum of the population risk.
Just to recap, it's just using the Hopkins inequality, right?
Yeah, just use the Hopkins.
So let's say if I'm training a neural network and I said that I want my weights to be bounded between 0 and 1, then would this apply? Would that
You should notice that here we require the function class to be finite.
yeah,
If you only say you bound the parameter from 0 to 1, you mean the norm?
the weights of the network.
You mean is either 0 or 1 or between 0 to 1?
0, 1.
So it's continuous.
Yeah.
Then there is
Okay.
infinite function class, and I will tell you how to handle this case.
All right.
Okay. How can we deal with infinite function class? One idea is that we can try to discretize the function class with some finite collection of representative elements. So for example, just as Gadami mentioned, if the parameter space is a unit ball, say that if the norm is less than or equal to 1, and if we want to bound the generalization gap, the uniform deviation for all the W in this unit ball. How can we do this? Use the discretization. Okay, I will show you. Given a ball, this is your parameter space or function class. There are infinity many. How to do that is that if we discretize the ball into some single point. Say if we have k points, from x1, from w1 to wk. Then we can use the Hopkins to bound the generalization gap in this parameter space, because it has its finite class with k size. But how to cover all the unit ball? On what? Base. But here we have k points. How can you? What do you mean by the base? Okay, the idea is that we consider to use these k points as a case central point to draw a ball. Okay, there are so many balls here. and the central point is just the W1 to WK. So if the radius is appropriate, then we can use these K points and is induced ball to cover the function class. Can you imagine? So now we get a larger function class, which is the union of all the of this K ball. Right, if I write it down this way. If say the radius is epsilon, then the union between this is the ball with central point W1 and radius epsilon. If we combine all these K balls by setting the epsilon appropriately, this can contain the unit ball. Right? Okay. So by using the Hopting, we already know that in each single point, we can have a generalization gap. What is remaining is that, what if the point is not in this finite function class? For example, given any W in the unit ball, W tilde. So since this is a cover for the unit ball, then we can find a ball, small ball, for example, B epsilon Wj, such that W tilde is inside this ball. So meaning that no matter how you pick a point inside this ball, there is a small ball to contain this point. Okay. And
Why we consider it as ball? Why we space the
yeah,
space of the function? Yes. Sorry.
because here the parameter space is okay. You can also consider the Q.
So it's because you restricted. So it's
Yeah. Well, also you can also use a Q. Depends on it, but here I just use the ball. Okay, so here we know the generalization gap in this function class. Now we are given any parameter or any function class inside this ball, because we can always find a small ball that contains this parameter. So the generalization gap of Wj is known, and if we also know the epsilon, if epsilon is also small, then ideally the gap will not change so much because the ball is very small and the central point has an explicit generalization gap. If we move, if the radius is small, then the gap will not move that much. This can be controlled. Yeah. So the problem is that if we are given a function, if we are given a ball in RD, if I want to cover, use a series of small ball with radius epsilon, how many balls do we need? So this is the problem. Depends on what? I mean, the worst case at the most. So this proposition tells us that the number of small ball is at the most 3 over epsilon to the d power. If we want to use a small ball to cover a unit ball in high dimension RD. And I will not show the proof here. So now we can have a cover on this unit ball by some finite small ball with no greater than this number. Then we can again doing the union bound, probability union bound, to bound the probability over this K finite data set.
The bound.
Yeah, so, okay. To answer your question, let's write the gap again. If we say the gap of one central point Wj is less than epsilon, how do we bound the gap for any W in the ball Wj? Is this what you want us? Okay, well, this is not hard if we assume that the loss function is Lipschitz. So you can see that the empirical risk is the setting the mean of the loss function. If this is Lipschitz, then this is Lipschitz. If this is one Lipschitz, then this is one Lipschitz in the parameter W. And also this holds for the aberration risk. So what do we only need to? Well, the Lipschitz continuous condition is not restricted. It's very general. So by the Lipschitz continuity, we can bound this term to be 3 epsilon, just by +1 -1 +1 -1. For example, this should less than minus Wj W. Right? This is epsilon. This is epsilon. The only thing that we need is this J. Okay. So this can be bounded to epsilon plus a deviation term. But this is fixed Wj. So we know that the Hopfing, this is square root of 1. Okay.
My based on the Lipschitz assumption, why can't you directly apply such process to the whole unit or then just use the pixel ball centered by centered with x I?
Can you repeat your question?
Here you can get the bound based on the assumption that the Lipschitz is right?
Yeah.
It's bounded, right?
Yeah.
Under what you apply such assumption for each ball?
Such assumption for I did not have an assumption on each ball.
No, but the Lipschitz for each ball, right?
Not for each for this loss function.
It's applied to each ball, right?
It's applied to a compact set. So given that the set is
applied to all the ball, right?
Yeah, all the 4 ball.
Yeah. Why you can't directly use it based on the assumption for this case? Why can't you directly use this similar process to the usual directly?
So you mean if we want to compute this term, you mean this one? How do you do that? You have some reference.
Oh, yeah. Maybe the easiest way is that calculus 1 from the top 1 center x 1 dot 1 no k 4 dot 1.
No, then this becomes this case.
Yeah.
This one? But this is not a small number. If you have, say, if this is Wj, then this is 1. This should be less than or equal to 2. This does not tell us anything if we only use 1. You see, we need this term to be small. We need the cover to be small. This is like a trade-off. We don't want the number of function calls to be small. Otherwise, the deviation in each ball is very large. And we also do not want the function calls, the number of function calls to be very large. Otherwise, the whole thing inequality will blow up. There is a trade-off. And here we just use this number. Okay, let's see what we can get. Suppose that the loss function is bounded with 1 Lipschitz in W. Then by the finite class result, we have just taking the probability union bound. This is less than or equal to epsilon. Then for any W hat in this function class, we can pick 1 inside this small ball. By some calculation we have inside this small ball, the gap is also very small. And combining these results, we can get a generalization bound for infinite classes via the discretization. That is, with high probability, the gap is like square root DON. Let me make some remarks. So this bound is dimension dependent. Well, which is not that good. Because if we want the generalization gap for this bounded for this function class to go to 0, then D cannot go faster than N. And the second remark is that recall that for finite class, the generalization gap is like log K. over n. If we ignore the probability eta, delta. And here this is for finite class, and for infinite class, the bound is like d over n. So how do we move finite from infinite? Then intuitively, this like if the function class k goes to infinity, then in the infinity dimension, or no, in the infinity function class, the complexity scales like e to the power d. D is a dimension. Right, so if this means that if the function class is infinity, then this the complexity looks like the e to the d power number of function class, because we can just use the finite class to get a bound. This is just a d. D is a dimension of W, because we want to cover a D-dimension uniball. O-tutor ignores the factor, logarithmic factor. So originally this looks like O, and I write this by O-tutor. Okay, this is the approach for the discretization. Another approach to handle the infinity function class is by Rademacher complexity. This is a complexity this is a measure to characterize the complexity of a function class. So in this discretization tools, the measure is just to count the number of the function class. But here the Rademacher complexity is another tool. So we have seen that the discretization generalization bound is dimension dependent, but the advantage for Rademacher complexity is that it can give a dimension free bound. Okay, so now let's look at a simple example. And through this example, I will show you what is the Rademacher complexity. Okay, this is a binary classification problem, and we have n samples with label either -1 or +1. And if the hypothesis class is given by some function from x to ± 1. Again, the decision boundary is by taking the sign function. If this is greater than 0, then this is 1. If this is less than 0, then the output of the label is -1. And we record the binary classification in the implicit bias that I used. This term YIFXI basically can be interpreted as the correlation of the predictor of F with the labels. So you can see that if the hypothesis function F can 100% classify all the points, that means this is positive. If this is positive, then this is 1. If this is negative, then this is negative. And then then this means this term should be very positive or very large. And if the hypothesis, if the function f misclassify all the data points, what happened? Then this is very small, very negative. Because if this is negative, then this is 1. This is positive, then this is negative 1. All the terms are negative. So given such a correlation, we can consider the ability of the function class f to correlate with random label. So intuitively, if a function class correlates with the random label, then you may think that this function class is very powerful, is very large, because it can contain the classifier even for random label. If this correlation is very small, that means the function class is not that powerful. The complexity is small. So here this is formalized by the random label is taking a random variable with just like so if this is 1 with half probability to be 1 and with half probability to be -1, this is a random label. And we define this quantity. The maximum correlation of the function class f to correlate with the random labels.
Random label means that in a theme X, the label can be different.
Here, the random labels means that the label is a random variable.
Yeah.
For example, with half probability to be 1, with half probability to be -1.
So given the theme X, this label can be
Yeah.
can be 1 or -1.
Yeah. This is a random label. So as I said, if this term is very large, I mean very positive, that means the function class is very large. If this term is very small, that means the function class is very small. In other words, if the function class is finite, the larger this term is, we can safely say the larger the size is. So this is the intuition for the Rademacher complexity. So instead of counting the number, we find an alternative way to quantify the complexity of a hypothesis space. And the definition is that given a family of function class f, given data sets, then the Rademacher complexity is given by the average correlation, maximum correlation over the random label. This is called the empirical Rademacher complexity. Average over sigma. Okay. So now given the Rademacher complexity, how can we use the Rademacher complexity to get a bound for the generalization gap? Well, I directly present the theorem. If this is if the function class is a bounded mapping, meaning that the mapping from Z to a bounded to the boundary value, then with high probability, this is the generalization gap is given by this form. So here this theorem uses the Rademacher complexity to bound the generalization gap. And the last thing, the only thing that remains is how to bound the Rademacher complexity of a given function class. If we can have a good bound, that means the Rademacher complexity is good. And next, I will give some examples on the Rademacher complexity of some concrete models.
Can you just go back to the definition, the Rademacher? So you can choose any distribution you want for sigma.
No, sigma is this one.
Is always the Bernoulli? The Bernoulli? That is the Bernoulli distribution. It's like either 0, 1, probability half.
No, this is either 1 or -1.
Oh, that is that one. Okay.
Special case. The special case of the distribution comes from.
Well, if you want to use some different random variables like Gaussian, 0, 1, standard and normal, you can also define a Rademacher complexity based on the Gaussian distribution. But there is a well-known inequality. I forgot the name. This inequality states that no matter how you choose the distribution of sigma, as long as this is mean 0, variance 1, or finite variance, then this term, the Rademacher complexity, are with the same order up to some constant.
Why is it not the modules, right? It's just a simple average. So the supremum can be negative. The Rademacher supremum, the supremum can be negative, right? Can be negative.
Yeah, if this function class is very small, then this can be negative.
So the Rademacher complexity only measures the richness of your function class. If the true correlation, then it's positive. The wrong correlation is
what?
negative correlation.
Negative
Yeah,
correlation.
you got the negative.
Then this is -1. If
Yeah.
this maps to negative.
If 0 is no correlation.
If this 0, then this is like a random
It's a
guess.
half.
So you're trying to correlate the random variable,
The random label.
the random label, with your approximation type. So it's like you want to see like how close your approximating function is with the random guess, basically.
Yeah,
Is that right?
yeah, right.
So you pick the function f in the space of functions that are most close, that's closest to a random guess.
Well, I mean, if a function class can fit the random labels, then that means the function class is very rich.
You have to explain the relationship between the sigma distribution and the results.
Okay. Oh, so okay, I get it. Then
Huh?
you're trying to choose f. Like if you say if in your space of function there is a function f that can approximate the flip of a coin, then your space of function is very rich.
Yes.
Yeah.
Okay.
Clear? Huh?
You have to explain the relationship between the distribution of sigma conform and the results.
The relation of what?
The distribution of sigma
It comes from this distribution.
You can, as you said, it can be Gaussian, right?
Yeah, it can be Gaussian.
So what's the relationship between the
That's okay.
You can use Gaussian.
So what's the difference, or what's the real meaning here?
Oh, for here, the sigma is the random variable, the flip point random variable. And you can also use the Gaussian sigma to get a Rademacher complexity.
No, but the whole point is that you want to use the distribution that has the highest entropy, you know, like that's the most random possible. So you choose the Bernoulli because it's like flipping a coin. You don't know if it's gonna be heads or tails.
Yeah, the intuition is that.
Yeah, but with
you
the
use-
Gaussian distribution first, it's concentrated in the means, so
Yeah,
it would not be as nice.
yeah.
So I guess the sigma should like relate with the data set.
Here,
Yeah.
so sigma is just a Rademacher random variable.
Yeah, because you want your like measure the correlation well. You're like, let's say the data set, all the data points are the same. Or like, yeah, all consider the extreme case. Then how do you choose the sigma?
No, this is expectation of sigma, the average case.
Yeah. I mean, how do you choose your sigma distribution? The sigma distribution should be somewhat.
In this definition, the sigma is exactly the flip coin.
Because you
Distribution.
consider the binary.
Yeah, this is the formal example is just the illustration why people consider the Rademacher complexity as this.
So this one is not the original Rademacher.
This one? This is.
The whole.
Yeah, this is.
This is what the x from the x sigma from the negative 1 or 1 is not. It's a general case. It's a special case of the original sigma.
No, it's just this is the original, and then people consider different kind of distribution of sigma, and then they find that there are some relations between these two quantities can be bounded by up to some constant.
So the only difference is the final result. Is,
Yeah.
That's the constant.
Yeah.
Can choose whatever it is.
No. Like, as far as I know, I only know the standard normal distribution, the flip coin
In
distribution.
this case, you cannot use the normal anyway because the function, because you're mapping to the binary.
Yeah, for the introduction, I will not use the standard normal because this is hard to explain. So I will use the -1, +1, because this is related to the random label. Okay.
But yeah, in this case, that also makes sense, no, because you just want to predict either 1 or -1.
Yeah.
So like the distribution that takes value outside of 1 or -1, in this case, might not be so useful.
Mm-hmm.
Yeah, just a comment. Just comment.
Okay, I think I should move on. So this theorem gives a bound for the generalization gap by using the Rademacher complexity. And now there are some examples to bound the Rademacher complexity on some concrete models. So the first one is the linear model with norm constraint, L2 norm constraint. In that case, the Rademacher complexity is of order 1/√n. So this is good because if we plug in this theorem and consider the unit ball function class, and if the function class satisfies this bounded assumption that this is of order 1 over square root n. But if you consider the first two use the discretization, still the unit ball, this becomes like the dimension dependent. So this is the one advantage for the Rademacher complexity.
So is the objective to drive Rademacher the complexity to 0? That are you trying to know? Are you the objective to bring the Rademacher complexity to 0? Make this as close as possible.
You want the Rademacher complexity to be 0?
No, like because of this theorem, you would like to achieve Rademacher complexity as close as possible to 0.
Yeah. If at least it should decreasing when the sample size increasing, because in practice, if we increase the sample size, we can get a better generalization.
So that's the same as saying that the f your approximating function is uncorrelated with the
Is correlated with.
no, but you want it to be close to 0, no? The Rademacher complexity.
Yeah.
So that's the same as saying the correlation is equal to 0 with the random variable.
Yeah, but that means the function class cannot be so large. No. Yeah.
So is that right to say that? To say that you want the complexity to come close to 0?
Yes.
So to say that you want the function class to be
Yes.
correlated as possible with the Bernoulli.
With the random labels.
Yeah.
Yes. Okay, so this is the next example is the L1 norm constraint. So this is some simple models that we can use that we can bound the Rademacher complexity. So now again, our topic is about deep learning. So the problem is that can we bound the Rademacher complexity on neural network models? The answer is this is still an open problem, because the bound is still sometimes not that informative. So here I will list one examples, the deep red-root neural network with Frobenius norm constraint space. So basically the deep red-root neural network is given by this one, where phi is a red-root. And if we constrain the Frobenius norm for each parameter, say Wi, the Frobenius norm is no greater than b, is bounded. And we also assume that the input has a bounded norm. So for this function class, Noah Golovich proved in 2018 that the Rademacher complexity of these neural network models scales like b to the k over square root n.
It's infinite case.
Hmm?
The infinite case.
What do you mean infinite case?
Similar as the k goes to.
No, here k is the size of the function class. Here k is the number of layer. So this is a k layer deep neural network with red-root activation.
So each layer has to be less than b.
Yeah. So for this function class, if we can see if k is 1, then this is, or if k is 2, for 2 layer, for shallow neural network, this bound looks good. Because for 2 layer neural network, the Rademacher complexity scales like 1 over square root n, given this constraint. But if we increase the number of layer, for example, if K is very large, and if B is greater than 1, then this term is bad, because this will blow up, making the generation bound vacuous.
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 What is it?
VAC.
Vacuous means meaningless. Means that the bound does not tell you something, because yeah.
So can you go back one slide? So to understand me better, like how do you get to the first result?
How do I get the first result? 1 over square root n.
Yeah.
Okay, I can show you now.
I mean, or just give an intuition. It's not strict.
The intuition is that by using some JSON equality. Okay, if you want to know, I can show you. Okay, so
Or 2 plus. Oh, you cannot add more than
no more than 20.
Maybe we can start a new book.
Okay, so for the first one, let's first write down the roundabout complexity is given by sigma. These right, this is the definition. And since this is a parametric function, then we can return this. We can rewrite this like smaller than or equal to 1. Right? Just to replace. So if we want to get an outer bound, then, well, we can directly use some inner product, Cauchy-Schwarz inequality. This is less than or equal to. This is. Right? This is an inner product of W2. And the superemment is given by the norm is 1. So this is exactly equal. There is no superemment. Sum. Okay. Now, let's use the JSON equality. So the fact, if x is a random variable, then, well, this is just a simple observation. The second moment is greater than the variance. Okay, so now we move on. Should less than or equal to take the square root. Okay, we continue. I from 1 to n, j from 1 to n, sigma I, sigma j, xi, transpose xj. Remember that sigma I is IID. Therefore, This is 1 to n. So if I is j, so if I is not equal to j, then the expectation is 0. So the only thing that remains is I equal to j. Sigma I squared xi norm squared. Okay. This is equal to what? For the Rademacher random variables, then this is just a 1. Sigma squared. The second moment is just 1. You can compute it. So then this becomes and we know that the input, the norm less than equal to 1. So therefore this is 1 over square root n. Now we are done.
So it's quite interesting, like that. If you go back to the theorem there, it's basically saying that it's just basically another way of saying that for the linear case, that
yeah, for the linear case, then in the linear model,
yeah,
if the input vector has a bounding norm, then the generalization gap will scale like one over square root.
It's a little bit it's very similar to the law of large numbers, right? Like if I took n to infinity, then
yeah. So as I said, the law of large numbers you need to notice that this is for a fixed classifier.
Yeah.
But this is for infinity class of classifier. We have a uniform deviation, a good uniform deviation.
Well, so for any classifier bounded between, so for any classifier for which the weights are between 0 and 1 in that case.
Yeah.
So this is more strongly the law of large numbers, basically.
Yeah. Okay. So we're back to the neural net, the Rademacher complexity for the neural network model. Since this is still a not perfect bound, it still encounters sometimes to be vacuous for if we increase the number of layer.
Why?
Yeah, width. Yeah, so this bound is because there are some constraint on the Frobenius norm. For example, for the WI, there is one dimension. This is the width. So this the bounding norm to some extent it has some constraint on the width. Because each parameter cannot be so large, otherwise this will blow up.
But if you have a deep enough network, it's already enough, like 10 layers or.
Yeah, then this bound is not that good.
Not so bad, right?
Yeah. So we need to consider other types of constraint, norm constraint, or other metric to obtain a non-vacuous bound for deep learning models. And there are some related works. One is by Peter Bartlett in 2017. This paper considered different type of norms. Say what different metric norm. And the second work is by Nishaba in 2019. This paper gives us a generalization bound for distance-based. So this connects the distance connects the optimization and generalization, because in some very large neural network model, since the number of parameters are very large, so empirically each parameter do not need to move much to get to the global minimum, local minimum. Then sometimes the distance will be small. So this paper considered to use the distance to have some constraint. And based on this constraint, this paper considered 2-layer neural network model.
You know, if in practice, has anybody applied some of these results in practice? Like,
Well, as I said, so this series of results is a guarantee.
the guarantee. Yeah,
So because we already know empirically, deep neural networks optimize well, generalize well, but how to explain it? What's the intuition behind this phenomenon?
for safety critical applications.
Yeah.
Have you seen any applications of these results or not?
I think this kind of statistical learning theory stuff cannot be applied to in practice.
Oh, you never know.
Okay, some further readings. Just to improve the generalization bound with different type of complexity measurement, such as the local Raman complexity, the Bayesian base, and the algorithmic stability base.
Because I'm thinking like if I wanna run a regression and I wanna have some boundaries on the like if I wanna compute the standard error of like a regression-based neural network, then maybe I could use that because like some of the regression problems that I have are not the networks are not very deep. So like I can say fix it in advance. And then maybe I could then compute. Then I could use maybe the results to compute like the bounds.
Yeah, you can.
Pretty cool.
Okay, we finally finished the boring stuff, generalization bound. I think maybe some of you guys are feel sleepy, but now I will move to a concrete example. I think this example is, some of you may heard about it. This is the star model that connects to the optimization with generalization called neural tangent kernel.
Star model. Say star.
Star model. So here I want to give you some gentle introduction of what is neural tangent kernel and how can we use the previous results to derive some results that match with the current result. Okay, NTK, we say neural tangent kernel to be NTK. So how does NTK arise? Well, now let's consider training a real valued neural network model FW by minimizing the square loss over the training data xi, yi from I to 1 to n. Now, if we write down the gradient flow dynamics, take the derivative dwt equals to negative gradient t. And if we use the FWT x to denote the function value vector and y to be the label vector, then by some simple calculus with chain rule, we can get the dynamics for the function value. Here the HT is a symmetric and positive semi-definite matrix with entry. The ij entry is given by the inner product of the function gradient.
What's GL?
Gradient flow, yeah. I introduced before. You forgot?
Yeah.
Did you forgot? It's just a.
No, I know what it is. I forgot what I I didn't know what was the acronym, but now you say gradient flow, I know what it is.
Oh,
Yeah.
okay. Okay, so the intuition is that if the neural network is very wide, the width is very large, then that means the number of parameters is very large. For example, millions of parameters. Then if we optimize these large neural networks, empirically the weights do not need to move much during the training. Well, this is just an intuitive description. If you only have a small number of parameters, you need to move to get to the global minimum. But if you have millions of parameters, each parameter only need to move a very
What does that mean?
move from the initialization. Yeah, I mean, for any fixed random initialization, you only need to move a short distance.
Its size is very limited, right?
Yeah, so here use the gradient descent with very small learning rate
Move towards where?
towards the global minimum or local minimum until it stops.
So for any random initialization, any fixed random initialization, the movement between the
Initialization to the
global minimum will be small.
Yeah, can be bounded.
This is the empirical results.
Yeah, empirical results.
Okay.
But also we will derive some results theoretically.
It means
Next.
you use some generalization, some generalization, maybe you can get a good result
You mean use the
Without,
distance bound?
without any optimization or any move, right?
Yeah, but you don't. But the optimization error is not guaranteed if you do not move. So the test error is still high. Okay, so based on this observation, we can use the first order Taylor expansion to express the function value FWT. Well, just to write down, this is a linear function, the first order Taylor expansion. And then back to this dynamics, HT is a matrix with ij's entry to this one. And if we use the first order Taylor expansion to approximate this function, and we take the derivative, then this is basically the gradient of as initialization. So here we say that the gradient of WT is approximated to be the gradient as initialization. That means the HT is approximate to the H0. And then under random initialization, as the width is very large, we can have some probability convergence. And one can show that in the initialized matrix H0 converges with probability to some deterministic matrix H. So this H is the so-called NTK matrix. Yeah, this is where the NTK comes from.
Can you show us why the gradient?
This one?
Yeah.
Because you can take a derivative. Right-hand side is this one. Left-hand side is this one. Right-hand side is this is linear on WT. Then. Well, to rigorously derive these things, you need some perturbation analysis. But here I just omit it there to show you how does NTK arise.
What's the NTK matrix? You gonna show us? What's the NTK matrix?
This is the deterministic matrix. Okay, I will show you an example. The NTK matrix. So consider a two-layer neural network. Okay, M is the width, also the number of hidden neurons. If M goes to infinity, that means if the neural network is very wide, then the NTK matrix is given by Hij. I mean the Ij's entry. If we restrict the input vector in the unit ball, then there is an explicit form. So this is a very simple matrix.
This is the NTK matrix.
Yeah.
One. What is that? One?
Which one?
No, like the first term. 1 minus r cosine.
Pi.
Pi.
This is 2 pi. R cosine xi transpose xj. But this is specific to ReLU. So for some other activation function, there is no explicit form.
But what exactly is this? Like why for now like you just said the NTK matrix. You just throw this name, but where does it come from?
So this is NTK means neural tangent kernel.
Oh yeah.
So why this is called NTK is because this entry is the inner product of the gradient. Well, by some limit. For example, M goes to infinity.
Oh, this is the definition of the matrix.
Yeah.
Oh, okay. That makes sense.
Okay, so now let's consider try to derive some optimization result and generalization results. So now let's replace the HT with a deterministic matrix. Then the dynamics of the predictions is given by a linear ODE. And then the convergence is guaranteed by just calculate the loss function dynamics, the LDT by some chain rule, given by this one. And this is a quadratic form. If we just take the minimum eigenvalue, then this can be bounded about by this form. And finally, we get a dynamics bound. dWdt is less than or equal to 2 minus 2 lambda Ln. So this then by some loss function is a squared loss. Then by taking the integral both sides, we can finally get a convergence rate for the loss function. This is the linear convergence. If we denote the minimum eigenvalue of the kernel matrix H by lambda 0, then it's like this one. One thing that you should note is that H is only guaranteed to be positive semi-definite, meaning that the lambda 0 may be 0. Then this convergence result is vacuous. So we should guarantee that the lambda 0, that the NDK matrix is positive. So for example, for this case, this is n by n matrix. If we restrict all the input x into the unit ball, the positive definiteness probability of property is guaranteed by each pair of xi, xj does not parallel.
So can you, now that you have the solution for the differential equation, can you just compute can you basically compute the value where it's equal to 0?
This is an inequality.
Yeah. But because you want to achieve 0, right? So could you find the value of t for which?
Oh, you mean find what exactly W infinity?
Yeah.
When t go to infinity.
Yeah, or when the expression reaches.
I will show it later.
Oh, okay.
Yeah. So this guarantees that finally the gradient descent when the widths are very large, gradient descent can converges to some global minimum. You can see when t go to infinity. But yeah, one thing that you should notice is that here we require that the lambda 0 is bigger than 0. So for this example, the positive definitely meaning that xi is not parallel to xj for each ij different pair. This is a very strong requirement in high dimension. A parallel is just this is xi, this xj, meaning that there exists some c such that xi equal to cxj. This means parallel.
Yeah, linearly dependent. Same as being linearly dependent.
Linear dependent.
Same as dependence, but they are linearly dependent.
You can say that. Yeah.
It's the easy.
Because actually the lambda 0 is determined by the minimum angle. If this is a ball, we say that this is restricted ball. X1, this is the center point, X1, X2, X3, X4, etc. So basically the lambda 0 depends on the minimum angle. If there exists some data vector that are parallel, that means the angle is 0. Right? This is x4. It's either 0 or pi, which is bad. Then lambda 0 is 0.
It's easy code condition to satisfy in high dimensional. Then it's easy code.
No, this is a very strong requirement. So actually, there are some works that bound because here you can see H is n by n matrix, right?
Yeah.
It determines by it depends on n. But if the data distribution is very bad, then it has a bad dependence on n. So there are some papers that studies the dependence of the eigenvalue on the data dimension and on the.
These are saying that the observations cannot be parallel. The observations x, x, and j cannot be parallel, right?
Yeah, this is the.
So, because like in statistics, sometimes when you're doing regressions, you have the concept of collinearity. So like you wanna remove all the variables that are collinear with each other when you're running a regression. So in the case here we have that you have the observations are collinear, right? So it doesn't seem to intuitionally doesn't seem to be such a strong.
Yeah, actually,
but then you just remove this the variables that are collinear.
Okay, so let's see what what happens if lambda 0 is 0? That means if you can imagine if H is a diagonal matrix, then basically in the image space, that means this is a orthogonal space of the kernel space. If this is for non-zero elements, we know that this is PSD. If we partition H into the image space, kernel space for image space, this is a positive definite. So in this space, this is a non-degenerate case. Then we have a.
But couldn't you just remove the variables, the observations that are collinear? There are parallel. Couldn't you just remove them from the?
Yeah, you can remove. You can also do not remove. Because for the
you want to avoid it from being 0, right? So if you remove them, then
yeah, then part of the dimension converges to 0, and part of the dimension does not. It remains the same, or that does not.
if you remove some of them.
Yeah, because you can see that if this is a diagonal matrix, right? For positive number, there is a negative, then this goes to 0. And if this is diagonal for the 0 kernel space, this is 0, then that means the derivative is 0. That means in the kernel spaces remains the same, do not change. So you can separate to be image space, kernel space. For image space, it's vanishing. For kernel space, it remains the same.
The random projection says that with high probability that the date when we project the data function, they are separate, right? So it means this condition.
No, this means for any two.
Two.
Do you mean that in high dimension, two random vectors are orthogonal almost surely?
Yeah.
Yeah, this is for two because we have n. We have n vector. If n is greater than d, you cannot find n vector distinct vectors that are orthogonal each other. Of course, you cannot do that. Okay, the last part. How do we use our result to derive the generalization results? The idea is very simple. Just first to bound the distance W0 and the final convergence parameter W infinity. I think Guilherme is also curious about what does W infinity looks like. And then based on this observation, we can derive a norm-based generalization bound. Because here the W infinity is contains all the possible global minimum that gradient descent can achieve in the NTK region. So this is the linear ODE, we can solve it. This is the good news. So to see this, we just write down the dynamics of WT. Again, it's equal to this form. And now we apply the first order Taylor expansion given by a linear ODE plus some bias term. And now if we scaling down the initialization magnitude by a large constant such that the initial function value is nearly to be 0, then this is like the linear regression problems or linear updating. The iteration is like the linear problems. We can directly solve this linear ODE. And then we can get an explicit form for W infinity. Now if W0 is 0, it's all closely to 0 because we can scaling down the initialization. Then this is nearly to be this one, square root 1 transposition inverse Y. So this is exactly the distance on the NTK region. And if this distance is bounded, then this correlates with the empirical observation that if for very wide neural networks, distance is bounded. The parameter do not need to move much to converge to global minimum.
Is it only one layer or how many layers?
No, this holds on the NTK region, any layer.
Yeah, I mean, but So what is the papers doing? Only one near.
You mean Aurora's this paper?
Yeah.
Okay, I will say. So we have a norm distance, and if we want to apply the Radon complexity to get a bound, what we need to do is to bound the Radon complexity on deep layer neural network with norm constraint. However, for deep neural network, there are some bad dependence. The Radon complexity has some bad dependence on the number of layers, as we see. So in this paper, Aurora considered over-parameterized the two-layer neural networks with ReLU activation. And he proved that the Radon complexity with norm constraint is bounded by all the distance over square length. This only holds for two layers. And then the generalization gap is dominated by distance. Square root the distance over square length.
Distance is the YHY, right?
Y transpose H inverse Y. This one. But this bound is still not good. It is because we don't know the order. We don't know the dependence of Y transpose H inverse Y over N, the order. This is we don't know because this is label dependent and also the underlying function dependent. So in this paper, the Aurora gave some examples on the underlying functions that when does the distance is order 1. So for example, linear underlying function, polynomial underlying function, and very specific nonlinear class function. But still, for the deep learning class data, deep learning data set or some other kind of like teacher-student network, if Y is generated by a neural network with nonlinear activation, this is not guaranteed to go to 0. But still, this is the first try that people try to bound the generalization for deep learning models. Okay, so here we see that the connection between optimization and generalization. So basically, the simple idea is that for optimization, we have a distance bound, and for generalization, we use the distance bound to get the generalization results. This is what people usually do. The weakness of the NDK, as you can see, it requires unrealistically large widths. And also the kernel methods don't match the performance of the state-of-art neural networks. Because if the kernel method is good enough, then why do we use the neural network? We can just use kernel method. So the advantage of the neural network compared to the kernel method is still not completely understood.
What do you mean? I don't know. How big is unrealistically large?
Usually, people tries to scale it. People tries to get a good dependence. For example, let's say if the width is m, then m should scale like the n to the 6th power. N is the sample size. So if, for example, if you want to train 100 images, and here I not consider dimension, you need like 100 to the 10 power width. This is unrealistic.
But if the weights are sparse, maybe you could compute some. some of the
Maybe, yeah. Then this is related to sparse neural network.
Are there results on that?
Yeah, then I think we are done. And now it's the conclusion part. So in this workshop, we give a gentle introduction of the deep learning theory from three aspects: approximation. This is the foundation for the success of deep learning. Optimization, this involves with some tools that allow us to train deep learning models. And the generalization refers to the trained model's capability to adapt to unseen data. And finally, we end up with a NTK model revealing the interactions between optimization and generalization.
Bravo.
Okay. Finally,
What says generalization?
which
Generalization.
Oh, okay. I can quickly introduce what I'm doing now. So basically, I focus on the interplay between the optimization and the generalization, because I think current all of the works that tries to get the generalization bound, for example, through the hybridization, through the norm constraint. For example, the norm constraint, the people usually consider the distance-based bound. But we found that compared to the distance, the length can be a better measurement, because intuitively, if you have intuitively, if you have two paths, this is the initialization. This is the final parameter. One path is like very oscillating, and one is very straightforward. So intuitively, we will say, even though that the distance is the same, the length is very large. It has very small length. We will say this one can generalize well. It is because the optimization is related with the data, or we can say the data manifold. If the optimization is very, very good, that means the data, one measurement is the condition number. That means the condition number is not that high. But for this case, then this looks like the data is very ill conditioned. So because this bound, the norm constraint bound, this is data independent bound. And the connection between the optimization and the generalization is not that clear. So we want to we want to build a more strong connection between optimization and generalization. So on the one hand, if the optimization is good, that means the data is easy to learn, and intuitively the generalization will be good. So we want to develop a length-based generalization bound, other than the length-based trajectory length, rather than the distance-based.
Length. Maybe you give some definition about the trajectory.
But isn't distance is the same? Like in English, isn't distance and length?
Distance is the if you have a trajectory, distance is the distance between the initialization to the final. Is
the shortest path.
Yeah, shortest path. But length is length, because the length contains the information how you optimize, and somehow you can say it contains the information for the loss landscape or for the data manifold.
To model the data manifold.
Yeah, this is a very hard topic, because currently we still do not have much tools to characterize the data. It's, for example, the data manifold. We just the information that we can use to characterize data is distribution, but sometimes we even do not know distribution. For example, I give you a CIFAR 10 data set. You cannot tell me the data distribution. What does it look like? Otherwise, you can use mean. Some moment. Of course, this information are not enough to characterize the data. So how do you describe the data? Is if you can describe the data with some tools, then I think these tools can be used to develop the understandings.
When you move the original distribution to the Python state, maybe it could be later or easier to follow the distribution automatically.
What do you mean by? Can you repeat your question?
I mean that because original the distribution of original data is equal to get or output. Well, if we more mapping or projecting the original data to Python dimension or other space.
Yeah, but usually in practice the data that we deal with is already high dimension. No. If we have like 10 dimension data, then we can of course project to a high dimension case. This is what kernel method doing.
So maybe it's not increase the dimension.
Decrease? Yeah, this is the case, but sometimes if you decrease the dimension, maybe there are some information that we'll lose. And also the thing is that which dimension you think you can remove? Though this is another problem. Okay. Thanks everyone. There is no audience in Zoom.
Thank you.
全是自己人。这个，这个。